I'm just verifying that my cluster is still in a running state and it looks good. And I'm going to go back to recent and I'll go to the 03 Data Analyst Pageviews notebook. Okay, so this notebook is relatively quick to cover. We should be able to finish this in like 25 minutes and then move into a different data set. One thing I want to do is take a really quick audience poll. I'm going to ask 3 questions, and I'd like you to raise your hand to one of those 3 questions. Actually, one question with 3 potential answers. So I'm going to basically ask you how you think the pace of the class is, and you can basically raise your hand if you, for the first answer will be like, if you think the class is moving a little bit too fast and you'd rather like the pace slow down so you can actually keep up. The second answer will be the pace is good, you're getting what you came here for, and you feel like you're learning enough without being like overwhelmed or going too slow. And the last answer will be like it's going a little bit too slow, like move a little bit faster because like you're getting bored maybe. Okay, so how many people here are in the first ballpark where you feel like the class is moving a little bit too fast, I've covered too much stuff? How many people here think the pace is good, so you're like able to keep up without getting lost? How many people here that think the pace is too slow? Maybe like move faster because you're getting completely bored. Okay, maybe a few people. Okay, so that looks good. This is kind of like what I was thinking about doing for the remainder of the day between 1 and like 1:30, finish up this page views, then get into clickstream, another data set, then take a break. After that, maybe spend a little bit of time on data sets and graph, and get into machine learning around like 3:30, and at the end of the day, do some streaming. So these are like blurry lines, but this is just kind of what I'm thinking about doing. And in order to make sure I can get into a little bit of graph, machine learning, and streaming, at some point, like at 3 o'clock, I'm just going to cut whichever lab we're in kind of short, maybe say a few words about it, just so we can jump into the other topics. Like I could probably be here and talk about Spark SQL for days if I could. But we're going to be a little crunched on time, so we'll just kind of keep moving. Okay, so if your cluster did terminate for some reason, then just reattach to it. Go ahead and hit Shift-Enter to run through all of these cells. Get to the first question. Make sure your Spark user interface is open. And let's go ahead and start answering a few questions. Okay. How many total incoming requests were to the mobile site versus desktop site? This is a different question than asking how many rows were for mobile and how many rows were for desktop. This is actually asking, if we sum up all of the 3.6 million rows for mobile, if you sum up their requests column, then how much do we get? So let's go ahead and do this. Let's import the Spark SQL functions. And then this is our Pageviews data frame. Just recall that the Pageviews data frame, if I do like a show 3, just remember what it looks like really quick. 3 columns, timestamp, site, and requests. What we want to do is for every time it says like mobile, we want to be able to like sum up requests to see how much it is. But to begin with, let's just do it for everything. So we'll do select the requests column, and then we're going to call the sum function on it, and then just do show. Okay, we have 13 billion actually is what this is. We have 13 billion requests over a 41-day period. How many are for the mobile site? See if you can figure this out. So remember, you're just going to do Pageviews data frame and then try to do the filter and then the show to, a filter and then a sum and then a show to see if you can figure this out. I'll give you like a few seconds to type this up. So how many of the requests were just for mobile? Okay, so to do this, I'll kind of work on it with you. You need to do a filter to bring it down to just mobile traffic. So we want to look for site, mobile. Okay, and that should just give us back a data frame. That should just give us back a data frame. And then after this, let's do the summation. So we'll select out we'll do the sum of the requests column, and then finally just show the results. Okay. Okay, so 4.6 billion for mobile. Let's copy and paste this and do the same thing for desktop. And remember, the answers for this are in the solutions guide. If you need to go look at that, feel free. Okay, here's, oops, let's do mobile this time. Desktop this time, actually. Okay, 8.7 million desktop, 4.6 billion mobile. So obviously Wikipedia gets a lot more traffic from the desktop. So this is where things get a little bit different, a little bit more interesting. What is the start and end range of time for the Pageviews data? So how many days of data is in the data frame? You already know it's 41 days of data, but how can we really figure this out programmatically? Recall, by the way, that our schema is thinking that the timestamp is a string. We should cast that into a timestamp so we can do date-time operations. So let's go ahead and do that. It's pretty simple. We take the data frame, and then look, this is all a select, basically. This whole thing until the end is really just a select. Except in this part of the select, we're pulling out the timestamp and casting it as timestamp. And actually, you don't need this alias here, so I'm going to delete it. You don't really need that alias part. So see, this is selecting out 3 columns, the timestamp, cite, and request. But for the timestamp column, we're also casting that as a data type of timestamp. This is going to convert it from a string to a timestamp. And we're going to call the data frame Pageviews timestamp data frame. That's all you need to do the conversion. And then let's print schema. And see how it now says timestamp? So now we can do, also if you actually look at the data frame now, see how the timestamp column looks a little different as opposed to a string? Okay, how many years of data do we have? In the Spark API docs, let's open this up. If you scroll down these docs, eventually after aggregate functions, you'll see date time functions right down here. So we're going to use some of these date time functions on our new timestamp data type column. Let's start with let's use the year. So let's scroll down. See this year? It extracts the year as an integer from the timestamp. So let's try that. From Pageviews timestamp, select the timestamp column, but then use the Spark SQL year function on the timestamp column, and then get a distinct on that and show. So if you want to see how many distinct years of data do we have. This should say just 2015, right? But how many months of data do we have? So copy this from above, bring it down to challenge 3, and see if you can change this to figure out how many months of data in 2015 we're looking at. And refer to the functions here to try to find which one you think would work to extract out the month. Okay, this one doesn't take really a rocket scientist. I'm going to change year to month. And it should say March and April. So our data is from March and April 2015. How many weeks of data? We can do week of year. So I think it's something like, let's see, I think it was like a handful of weeks. So week 14 till week 16 of data. How many days of data? Let's do day of year distinctly. So there should be 41 days of data. See how we're counting that? That's why we're seeing that. If we don't do a count and instead do a show, then we should be able to see exactly what those days of year are. See, it starts from 77th day of 2015 all the way till, I think maybe actually no, show only shows you 20 results. So to see all 41 days, we would need to wrap show with a parameter, 41 days. Or we can just do 50 and we'll only get 41 back. And we should probably do like an order by to see that in order. But it's basically 41 days of data, and you can kind of see that there. Okay, so that's a bunch of date time type of functions. We can do some statistical functions like average, min, max. So we're going to look at average, min, max data for mobile, select out, requests 3 times, but we're going to look at average, minimum, and max for requests. Okay. For mobile, average is 1,200. Let's do the same for desktop. For desktop, average is like 2,400, almost twice as much traffic. You can see the max for mobile in a 1-second period was about 3,000 requests. Desktop, about 5,500 requests. Yes?
What is the predicate using only a single equal here between desktop versus triple?
There's multiple ways to do this equality check. This is one way you can also do it, but you can still do it the other way if you want. It's just whatever preference you have. Yeah, so this will work as well. So it's just whichever one you want to use. This is what I recommend using, especially when you have multiple confusing arguments. Why didn't that work? Oh yeah, you have to do triple equals now. So, same thing. Which day of the week does Wikipedia get the most traffic? Okay, so here's where things will get interesting. What day of the week, like Monday or Sunday, what day does it get the most traffic? So here what we're going to do is, here's just some boilerplate code I wrote. We're going to take the data frame, group by date format of timestamp E. What this means is E is basically the pattern in the simple date format class to pull out day of week, like MON or TUES. Like, we're going to pull that out, call that column day of week, sum it. Let's go ahead and run this and just see what happens. We're going to sum it, get the Pageviews day of week data frame, register that as a table, cache it, and then show the results of Pageviews day of week. So this is basically the main thing we're running. And then I'm just caching it because in the future I might want to look at that data multiple times. Okay, there we go. So this is a really tiny data frame, but this is confusing for me to look at because I want to do I want to sort this in order from like maybe Monday through Sunday. So how can we do that? I can see in general that Monday seems to get more traffic than the other days of the week, which is interesting, I guess. But I want to change the day of week column so that it's in order. So this is where we'll use a user-defined function to basically tack on a number before these days of week. So we'll make Monday be 1-MON. We'll make Tuesday be 2-TUE. That way, then when we order it by day of week, the number will actually order that row correctly. Because right now it's, I did do a, actually, well, we can try doing an order by really quick and you'll see what will happen. If I do an order by, like right here, and then go to table, you see it's actually doing it alphabetically, so F comes before M, which comes before S. That's not what I want. I want it to go from Monday through Sunday. However, I can click on the bar graph here. So I had just clicked on table, but I can click on the bar graph and I can see that Monday seems to get more traffic, but this is out of order. So let's make a UDF that's going to change the data in the row here and append it with the number. So we're going to make a simple user-defined function to do this. Okay, user-defined functions. This is a Scala user-defined function. Basically, we just have a Scala match expression here called match day of week. It takes in a string and it emits a string. When it takes in a string called day, all it does is if it sees a MON, it's going to emit 1-MON or 2-Tuesday. So that's our Scala method right there. Let's test it by passing in Tuesday. Yeah, there we go. What if we pass in Monday? So MON. Okay, it looks like it's working. Let's try Saturday. Yeah, it's definitely working. So here's how you define a UDF that you want to use. SQL, context, UDF, register it with this name. It takes in a string and it emits the results of that function. And this is called we're going to name it the prepend number UDF. And this is how you use it. Page views by day of week, that's a tiny data frame we had with 7 rows. We're going to select out the day of week, but notice how whatever it gives us for day of week, we're going to wrap it in the prepend number UDF and then do show 7. And now we should see, yeah, there we go. That looks better. We still need to do an order by, though. Okay, so let's do the same thing. This time what we're doing is instead of, see the name here? It says UDF day of week. We're going to give it a prettier column name. Okay, so we're taking our data frame and we're making a new column, basically. Some requests, we're going to rename that to total requests. And then we're selecting out the day of week. Let's go ahead and run this and just look at the results right there. Okay, so that's basically what we did with our UDF. So there's no function in Spark that can take MON and give you 1-MON. We had to write that custom. Now if I look at the bar graph, it's in order now, Monday through Sunday. Do you guys think this makes sense that on Monday, Wikipedia would get so much more traffic? Yes, maybe people come back from work or the weekend or something. Maybe it makes sense, maybe it doesn't. I thought it was interesting. We'll come back and investigate that in a little bit. Yep. What is the extra register step doing? You have to register it before you can actually use it like this. See? Oh yeah, so this name is actually used if you're going to use Spark SQL and write a SQL query. Then you would use this name. If you're using DataFrames, you would use that name. Okay. Can you visualize both Monday mobile and desktop requests in a line chart and compare traffic to both sides by day of week? So for this one, there's just some boilerplate code here. You've seen all this stuff before, so I'm not going to cover it in depth. I just want to show you that you can graph stuff really quickly. So you can kind of go through this if you're interested, but you've seen most of this before. We're basically filtering it out for mobile traffic, and then we're doing the same thing we did before to generate the graph. Okay, so if you look at this, this is just mobile requests, and then we can make, this is just making a mobile data frame. See this? Mobile views by day of week. This is what the mobile views by day of week looks like. But we want to make a unified chart with mobile and desktop requests. So we'll do the same thing for desktop here. So then we're going to have a desktop views day of week. It's just seven different rows for desktop. And then we're going to do a join. So this is something new. We're taking the data frame for mobile views, joining it with desktop on this column, on the day of week column, because both data frames should have the 1-MON, 2-TUES, or TUE. So we're doing a join here, actually. And after we do the join, let's just look at the table first. This is what the table looks like after the join. It's a pretty simple code, really. And then we can plot this by hitting the line graph here. You can also just hit the line graph and then kind of see this. And you can go to plot options to see how I did the keys and the values to make the graph look like this. Okay, let me cancel out of this. Okay, so this looks cool, but one thing you might notice is this is really deceptive. This makes it look like the mobile requests are almost 0, but it's not, right? The y-axis starts at 600 million. So what if we wanted to make that y-axis start at 0? It's not possible to do that in Databricks. So what we'll do is we'll jump into a different visualization library, Matplotlib. We'll do that really quick. I'm just going to run through this part in like 2 minutes because I don't want to teach Matplotlib. I just want you to see how you can use a Python visualization library. And then we'll come back and think about that Monday question. Okay, so we'll skip through this. We already did this. We're going to come back to question 6 in just a minute. Not yet. Let's just do this bonus stuff really quick. I want to show you that you can basically, in the Scala notebook, even though there's a Scala notebook, you can do %Python, and then you can run Python commands. So here I'm making a Python function to do simple math to sum up x and y. Just notice that I can make this function, then I can call the function here in this cell. So see, I'm passing in 2 and 3 up there, and I'm getting 5. So you can do Python in a Scala notebook. Here, we're going to import Matplotlib and make a little bit more sophisticated of a plot. So I'm not going to cover this in depth, okay? So just notice we're bringing in NumPy, Matplotlib, and doing some plotting. This is just a fundamental basic plot, just to make sure it works. This has nothing to do with our data. And then we're going to use these 2 data frames, and we're going to plot them in Matplotlib. So just kind of pay attention to this demo. You don't need to even do these cells. Just kind of look at what I'm doing really quick. We're going to graph just the desktop views by day of week initially. I've kind of manually typed in the numbers here, but in a second I'll show you how to do this programmatically. But just to keep it simple, I did it manually here.
Is this just using the system version of Python, or is it whatever's on the cluster?
It's whatever is on the Databricks cluster, whichever library we have. Okay, this is desktop views. This is mobile views by day of week down here. Now, next what we'll do, we'll combine the 2. So, okay, this code shows you how you can take Scala data and bring it into Python. The way you do it is you hand off the data to a temporary table. So I'm taking these 2 data frames. This is a Scala cell. I'm taking these 2 and I'm registering tables. And then in Python, look, this is a Python cell. In Python, I'm reading that data. I have a Python data frame. And in the Python data frame, I'm running a collect to get a list. And then I'm traversing through that list to basically get a Python list of mobile requests. See how I did that? This is how you go from basically taking Scala data, you do a handoff to a table, then you read that table using Python, like this. And then I'm going to do the same thing for desktop. That's my desktop list. And then I have a Python list there, and I have a desktop list of requests. These are just Python lists. And then finally, this final cell shows you how you can plot them both together. So once again, I'm not going to cover this really in depth. You can review this on your own time. But here we go. We have now desktop requests and mobile requests together. And we can see now that it's used a 0 index for the y. Right? So you can come back and review this on your own time. What I do want to do right now, though, is I would like you guys to work on the hardest challenge so far, which is question number 6 up here. Spend like a few minutes on this, and then we'll move into another data set. So what I want to do here is come up to question 6, and then do this. Open up like a bunch of cells, like 5 or 6 of them, by hitting this plus button. And then see if you can figure this out. Why is there so much more traffic on Monday than other days of the week? Okay, this is going to require some creativity and a skeptical mind. We can, one thing we can do actually to make it a little bit easier for you guys is, here, let's do a quick a theory type thing. So what theories might you guys have? So let's do this together, and then I'll let you guys actually try to figure this out. Theories, I think I spelled that correctly. Okay, so let's come up with a few theories about what could be going on. So I'll take some, you guys can start yelling things out. I mean, one thing I'm going to say is maybe Monday does really get more traffic. Okay, this means there's nothing wrong with the data. Are there any other theories that you guys can think of for what you can maybe look at to try to figure this out? What's that? Yeah, bot schedule. So maybe like Google, Bing, bot traffic is high on Monday. That's a good one. Are there other theories you guys have?
Maybe there are more Mondays.
That's one of the best ones. Maybe there are more Mondays in the data set. We didn't check for that. What else do you guys think?
Cleaning operation by the area.
What's that?
Some kind of cleaning operation.
Okay. What do you mean by that?
Remember you gave us an example at the beginning, correct, malicious, like that.
The what?
Someone wrote something bad and then they cleaned up.
Okay, so maybe it's a cleaning operation. One thing somebody in another class has said that it was like maybe something to do with daylight savings time. I don't know. I'm just typing random theories up right now. Web crawler start Monday. We talked about that. So this is bot traffic or web crawlers. Are there any other theories?
Maybe time zone?
Time zone issue. Okay. So you'll have to like be creative about how you can solve this. What I'm looking for is for the first person who can definitively tell me what the problem is. Not a theory, but show me in code that you've solved the problem. Okay. Any other theories you guys have? So basically, we're doing exploratory data analysis, right? So like we want to kind of see if we can attack this. See, okay, so go ahead and take a few minutes. This is some good places to get started. And I'll give you a few hints along the way. This is going to be like just a 4 or 5 minute exercise. Using everything you've learned so far, see if you can figure this out. It should be a fun little challenge. And feel free to work with the person next to you if you'd like to figure this out. I'll give you a hint as well. I'm going to give you one more thing to help you guys. These two are page counts files from a specific day. Actually, let me not show you that just yet. Just kind of, let's wait. Let's wait to see what you guys come up with, and then I'll give you some hints along the way. So the first thing I would recommend looking at is, are there really more Mondays? And is there like a spike on a specific day for some reason? Try to like look for that kind of stuff. If you think you have it figured out, just kind of let me know. Raise your hand and tell me what you think it is. Anybody know what's going on? Not yet. I usually have Spark stickers to entice you guys, but I can't find any right now. There's a huge outlier on one day. Which day? Day number 110. Does anybody know which day that is, the huge outlier? Does anybody see a specific day out of the 41 days that has a huge outlier? Tell me what day you think it is if you see an outlier. What's that? I can't hear you. April 20th, indeed. Let's try to figure out how you did that first. That doesn't fully solve the problem, but you're getting close. So if I do Pageviews timestamped data frame, let's start with that one. Okay. I want to look at, I'm going to do a, hang on. Here's the way to do this. I'm just going to kind of copy and paste the code here. Okay, I'm going to group by day like this, by day of week. So what I'm doing is just a group by like this, by day of, actually by day of year, and then sum order by sum request show 41. Let me just show you what this looks like. So I'm starting by just checking how many requests are happening each day out of the 41 days. And I've ordered by the sum request. So there's, okay, like what is that? 187 million, 289 million these days. So in general, it's about 300 million. These are all 300 million every day. Let's keep going and seeing if there's any really large days. Okay, if I scroll down, look at this. The 110th day has 665 million requests. Everything else had under 350 million requests. So what is going on with the 110th day? Why does it have so many more requests? See if you can kind of figure that out. It's a what? What day of the year is the 110th day? It was what? Day of week. Oh. Okay, so yeah, April 20th, let's see. But we want to look at April 20th, 2015, right here. So that is a Monday, April 20th. This is like what was going on, I guess, in the world on that day. So we are looking at a Monday. April 20th is a Monday in 2015. So what happened on that Monday? Is that like natural for that to have happened? See if you can continue this logic. There's a little bit more investigation you'd have to do to get to the root cause here. If anybody figures it out, just yell it out. And I'll leave that code up if you want to see that right there. So one cool thing I made actually is, remember the page counts data we were looking at? I actually, maybe you'll need this, maybe you won't. But I also have page counts data for April 20th, 2015 at 3 p.m. and at noon. So you can get to this data, like, here, let me show it to you. If you do %fs ls, and if I want to look like at the noon data for page counts, remember the first lab we did for page counts? Oops. Actually, it's under, I need to do the full path, hold on. One second. I think it's under Wikipedia, read-only, page counts, and then let's see. I think it was under one of these. No, actually, just right here. Okay, there it is. So this is the path for the noon 1 hour file and the 3 p.m. 1 hour file. I'll just put these up here, right here. So, I mean, this is interesting data. It's all real data from the Wikimedia Foundation. So if you think that, I mean, the reason you might want to look at these files is maybe you can find out what's going on and what caused that spike. Like maybe it's natural for that spike to be there, and you can figure it out by looking at these files. Or maybe you don't need to look at these files. I don't know. This could not be useful. So see if you can figure this out. Does anybody know what's going on April 20th? Start diving into the data for that day, either through the Pageviews file or maybe the page counts file for the 2 hours I have there for that day, and see if you can figure it out. I'll give you the answer in a minute if nobody does. What's that? There's duplicates in the data, exactly. How much data is there for each second? Yeah, I mean, you actually did get it right. Let me show you that. So here's what we'll do. We're going to take that normal data frame, we're going to filter it by day of year and keep only the 110th data, 110th day of data. Okay? And then on that data frame, we can run a filter and look at just midnight on April 20th. Okay? And then we'll run show. And let's see what we get. So April 20th at midnight, we should get 2 rows, right? We should have a row for mobile and a row for desktop. Look at what we have instead. 2 rows for mobile and 2 rows for desktop. So for some reason, this data itself has duplicated data. I mean, look, if I go to 1 second after midnight, will be the same thing on April 20th. See how there's duplicated data? But look, if I go to the earlier day, the 109th day, and go to like April 19, and then look at 1 second after midnight, let's look at this. So the earlier day. Now I only have what I'm expecting, 1 row for mobile, 1 row for desktop. If I go to like even midnight for April 19th, I'll have just 2 rows. But basically what the solution here is that for some reason, the data on Monday is duplicated for April 20th. I'm not sure like why. I mean, this is a file that was directly downloaded from the Wikimedia Foundation. I don't know if this was like a Easter egg they put in the data or if it really was some malfunction in their system that caused it. I'm not really sure. But I guess the point I hope you take away from this is to be kind of suspicious with what you're doing and don't just, graph something like we did in the beginning and interpret that to mean Monday really did have a spike. Another thing that happens actually is that in this data, if you keep investigating, you'll notice that you have, I think it's something like there's 6 Mondays, 6 Tuesdays, 6 Wednesdays, but I think there's only 5 like Sundays. There's like 1 less Sunday, which is why you have that dip on Sunday as well. So if you remember from the way we were seeing the graph, actually maybe not that one. If you look at the first graph that we made, like this one, there's actually less Sundays in the data set than there are other days of the week. So we basically have like something like 6 Mondays, Tuesdays, Wednesdays, Thursdays, and Fridays and Saturdays, but I think there's like 5 Sundays or something like that. So there's like a few different problems here. And I think even for Saturday, for one of the Saturdays, we only have half the day's data for Saturday. So like Wikimedia Foundation just like stopped collecting in the middle of a Saturday, I think, the data for this. Right, so there were like a handful of problems with this data, which we should have properly investigated before we made this specific chart. Okay, any questions about any of that?
No, I mean, Mark, it's kind of funny that it's decreasing throughout the week, though.
Say that one more time?
It's kind of interesting that it seems to be decreasing throughout the week, right?
It kind of is. Really, like I said, Sunday has less days of the week, so really Sunday should be higher. Saturday, for one of the days, we only got half day, so that should be higher as well. So it should really all be around this much. So it's really not decreasing. We just have bad data. I mean, if you think about this, a global top 10 website should not be seeing this type of pattern. You can't justify this because only in like Western countries do you take a day off on Saturday and Sunday. In like the Middle East, for example, the weekends are actually Thursday and Friday. And the pattern should be kind of uniform for a top 10 website. So you should have been kind of skeptical as soon as you saw this. It's not fair to just kind of reason and say, oh, well, maybe people come back to the office on Monday and are looking at Wikipedia for some reason. That was kind of like a diversion I tried to throw at you, I guess. All right, so be skeptical. I might pull something like that on you again. I don't know. Any other questions?
You should also do this by time of day as well. It'll be interesting to see whether it's...
Yeah, but then again, I guess you could do it by time of day, and maybe since we're looking at English Wikipedia, when the sun is up in the US or in like England and American-speaking countries, then you're probably getting more traffic. But yeah, when the sun is up in like Japan and China and Russia area, you're probably not going to be getting as much traffic. Yeah, that is true. Any other comments or questions? Okay, so let's move into a different data set. We'll move into the clickstream data set, which is my favorite data set, actually. So let's go to the RunMe folder for 04 data analyst clickstream. Okay, so we're going to go to the clickstream data. I'm going to close out of the Spark user interface, and I'm going to attach to my cluster, and then restart the cluster. I'm attached, and then do a restart. And that should be restarting. As it's restarting, just kind of skim through what's going to be happening here. We're going to work with a different data set. It's 1.2 gigabytes. These are some of the questions we're going to answer, so please skim through this, the business questions. And then also look at the technical accomplishments here. So these are the kind of things that we'll be covering. And this lab, I'm going to probably only cover about 50% of it, and then I'm going to jump into something different. Because some of the stuff here is repeated knowledge from before. And since this is a kind of advanced class, I want to move into machine learning and streaming rather soon, in like about an hour. Looks like my cluster is almost started. And then as soon as it's up, I'll just open up the UI again. This is clickstream data. It's 1.2 gigabyte tab separated value file. There's 22 million rows in this file. And it contains about 3.2 billion requests information from February 2015. Looks like I'm started. I'll open up the UI. It should be empty. Yep. Okay, so this only includes requests for articles in the desktop version of English Wikipedia. So what does this mean, 22 million refer resource pairs? Let me explain. Like I said, remember there's 22 million rows, okay? Let's do a ls on this so you can actually see the file. So we're just like running the magic %fs command for file system, and we're listing the contents of this directory, and there it is. See, this is a 1.2 or so gigabyte file. It's a single tab separated value file. Okay, so this is what the data is. Imagine that somebody goes to the Apache Spark page, then they click on this University of California link. And then they get to this page for UC Berkeley. Then maybe they click on the California page. They get to the Wikipedia page for California. Then they click on United States. And then they get to the United States page. So this is like the click stream of somebody traveling through the pages of Wikipedia. This is essentially the kind of data we're looking at. We can skip this cell and go ahead and read in the data. So we're going to use the Spark CSV library to read it, delimiter tab, infer schema, and basically give me a data frame called clickstream df. Okay, that's running. So this is a 1.2 gigabyte file. How many tasks or how many partitions do you think will be created? Well, basically 1.2 gigabyte divided by 64 megs, right? Each partition. It would be something like maybe 18 or like 19, I guess, tasks, something like that. 19, 20 tasks should be required. So if you look at how many we're using, this first one is just inferring schema, and then we're actually using 20 tasks to read this data. You'll notice we're running 3 tasks at a time because we have 3 slots. So it's a 1.2 gigabyte file. Basically, each of these 20 tasks is reading about 64 megs of data. Okay, and it was just looking at schema right there. Let's do a display to take a look at the data. This is what it looks like. Okay, so let me explain what this is. We basically really care about the previous title and the current title. These are the 2 titles. Somebody clicked from this title to that title 11 times. Or, Loud and Up Now is just an article in Wikipedia. It's like an album for a music band. And 19 times in February 2015, 19 times somebody from this page clicked into that page. Okay, so that's what this data basically means. So that's what the refer resource is right there. This is like the refer right here, and this is the resource right here. And then if the referrer is a Wikipedia page, then there's going to be an ID there for the Wikipedia page ID. But if the referrer is like a search engine, like Google sent traffic to this page, then there's no previous ID, but there's always going to be a current ID because that's the Wikipedia page that somebody went to. So there's 22 million rows. That's what that means. And if you sum up this n column completely, then you'll get 3.2 billion. What can be in refer? Resource is always going to be a Wikipedia page name. But for referrer, sometimes it's a Wikipedia page name. Other times it's like search engines. So let me explain what the referrer can be. If it's a Wikipedia article, it's just going to say the article title. Other Wikipedia means any Wikipedia page not in the main English namespace. Like somebody from their user page sent traffic to Wikipedia, then the actual article. Other internal means a page from any other Wikimedia project, like Wikibooks or Wikinews. That's what other internal means. Other Google, other Yahoo, and other Bing is self-explanatory. There's also social networks that can send traffic to Wikipedia articles. Other empty means HTTPS encrypted traffic. And other just means anything else, like the New York Times or BuzzFeed or something like that send traffic. Okay, this is the only thing that can be in the refer column is one of these things. And for article title, it can be one of the 5.1 million articles in Wikipedia. But if it's not an article, it's going to start with other dash, if it's not an article that send the traffic, okay? And like I said, n is just the number of occurrences of that pair in February 2015. Okay, does everybody basically understand the data? And you can like download this data from Wikipedia as well. We'll cover type in a bit, but basically with type, as long as it's an article that's doing the link, it's going to say link. If it's not an article, so if like the previous title is not an article, it'll just say other. All right, we'll come back to that later and explain that in more depth. Okay. So we covered all of this. We can print the schema again if you're interested. You can see how we inferred the schema there. And this basically explains all the columns if you didn't catch what I just described. We're not going to need these 2 IDs, so let's delete them. We don't need these 2 IDs for our analysis in this lab. So what we're going to do is, in our clickstream data frame, let's only select out the 4 columns that we care about. We don't really need those first 2 columns, not for this lab. So we'll just make another data frame called clickstream no IDs data frame. And then let me just show you what that looks like. We just basically got rid of those 2 columns. Okay, now before we actually look at this data, I would like to cover a little bit about the Databricks and Spark architecture, because this is going to help us to do some of the more advanced things. And then probably after this, we might take a short break. Okay, so this is a refresher that you're working on a 3.7 gigabyte JVM with 3 slots. There are 9 other containers on this machine. This EC2 machine is a R3 2X large machine. It has about 60 gigabytes of memory and 8 cores, 8 vCPUs. And we're basically oversubscribing the vCPUs because, you know, we have actually 3 slots times 10. So we have like 30 slots running on this machine, but each of your notebooks is isolated within the specific container for your cluster. So let's explore this a little bit. In Databricks, if you run %sh, that lets you run command line like bash commands inside your container. So you can just run like Linux commands. That's kind of a cool trick. So let's check how much memory is available on this machine. On this machine, there's 60 gigs of memory on this EC2 machine, and there's something like 31 gigs free on this specific machine that my container is on. Let's do JPS. This is going to tell us how many Java virtual machines are running in this container, in my container. So when you run this command, you can ignore the JPS output. That's just my JPS command running. Driver daemon is actually the 3.7 gigabyte JVM. This is the actual process ID for the 3.7 gigabyte JVM. Chauffeur daemon is something different. This is like a Databricks thing. I'll show you what that is in a sec. You can also run JPS with verbosity turned on. And then you can see things like, you can see that the chauffeur daemon on process ID 617, you can see that the chauffeur daemon basically uses 1 gig of data. It starts with a 1 gig JVM, and it can go as big as 1 gig. However, the driver daemon, this is our actual 3.7 gigabyte local mode cluster. The driver daemon starts with 3.7 gigabytes of memory, and it can grow as much as 3.7 gigs. So what's chauffeur? I guess that's the last mystery. Chauffeur is a special Databricks feature. It's a trick we have to allow you to basically have 5 different notebooks connected to the same cluster. So in this local mode cluster, we allow and support like 5 REPLs, for example, in this diagram. We have 5 REPLs, therefore 5 different notebooks can be attached to the same cluster. This is the trick we use to multiplex commands running in different REPLs in the driver. Right? This is kind of a Databricks-specific feature. If you, for example, have a Spark local mode cluster running on your laptop and you're running like Jupyter notebooks, you can only attach 1 Jupyter notebook or Zeppelin notebook to that cluster. So this allows us to go beyond that limitation. So that's really all that is. Yes? I believe so, yeah. You can cache that table and somebody else in a different notebook can access that data. It's a shared cluster. Here, if you click on the Executors tab, I already showed you this. You can see how much memory is potentially usable for caching. Right now, I didn't cache anything. Another cool thing you can do here is actually you can take a thread dump of the executor. Well, right now I have the executor ID shows up as a driver because this is running driver and executor code. But if you click thread dump here, you can see all the threads that are running in this 3.7 gigabyte JVM. See these worker threads? They're in an epoll waiting state. These worker threads are the ones that will actually run on those 3 slots. Everything else is just like an internal thread that Spark's JVM is using for housekeeping or garbage collection or something like that. The rest are all internal threads. These ones that say worker IO, these are the ones that are actually going to run your actual code. I guess I can show you that really quick. Let me do a quick demo. Not this cell. This is just saying that our data frame currently has 20 partitions. Let's repartition it into 6. Because that's a better setting for our cluster. Let's repartition it, and then here's what I'm going to do. I'm going to run this cell, and now that, well, this is a lazy operation, so nothing happened yet. This is registering a table called clickstream, and then this is going to actually materialize the repartition to happen and the caching to happen. Check out what I'm going to do right now in this cell. I'm going to run count, and then I'm going to take a thread dump, and I'm going to show you those 3 cells, those 3 threads, which will not be in a waiting state anymore. Okay, so I'm going to go ahead and run this count. Okay, my Spark job is running, and 3 tasks at least are running right now. Let me go back to the UI. Okay, notice right now the coloration here, okay? I'm going to now go back to executors and click thread dump, and then look at what will be different. See how now these 3 threads are in a different color and it's in a runnable state? I can expand one of these, and I can see that this specific one seems to be doing something with the Snappy library, and it's doing some like Java I/O. What about this other thread here? This one is doing something with CSV parsing. All right, this is a way to basically look at hotspots in your code to understand why a specific thread might be taking a long time. And I usually like to run that several times to see how that changes. So you can kind of see what's going on in each of those threads, like the full stack. And it looks like we are now in the next stage. And you'll notice these 3 are a different color. So hopefully that will be useful for you at some point if you need to troubleshoot why something is running slow. Basically what you'll see is if maybe you're like, calling a UDF or something, and that's what's slowing you down. If you take a thread dump, you'll see that UDF function at the top of the stack. That's how you know that's what the expensive part of your code is. Yes? That's right. You have a JVM of 3.7 gigs. However, in that 6 gigabyte container, so yeah, the JVM is 3.7 gigs. Chauffeur is 1 gig. That's 4.7 gigs. But there's still extra room before you get to 6 gigs. What else is in there? Well, there's actually also 3 Python processes, which I'm not really covering since it's the Scala class. But to explain what's also going on here is in here, let me use a simpler actually, I'll use this one. Okay, yeah, this is a 6 gigabyte container, which has a 3 gigabyte JVM and 1 gigabyte chauffeur, and there's actually 3 Python processes in here. 3 Python processes because you have 3 slots here. And each one of the Python processes is 512 megabytes. If you had written a Python UDF, that Python UDF is going to run in the Python processes, which is going to run significantly slower than if you actually wrote that UDF in Scala or Java that would run natively in the JVM. So Scala UDFs run in that JVM. But a Python UDF is a little bit more complicated. What would happen with a Python UDF is Spark would have to actually take the data from the JVM, uncompress it, pickle it, and then send that pickled data to the Python process, and then run actual Python UDF there, and then take the results back and send it to the JVM. And that's going to slow you down significantly. That's why Python UDFs are significantly slower than Scala or Java UDFs. So that's basically, then you're getting close to 6 gigs when you consider the 3 different half a gigabyte each Python processes. You can check that, by the way, by running like PS in here, to look at process. I think it's just PS in Linux. And you'll see some Python processes, basically. There's 1, 2, and there should be 3, actually. There's the third one. Those are each 512 megs, and you can see there's actually a few other processes running here. Okay. Okay, we'll take a break in just a minute. What I want to do is just complete this section right here so that we can get to, when we come back from break, we'll start at question 1. But let me just finish this section really quick in the next few minutes. Here we have a clickstream data frame with 6 partitions. Why did we repartition it and make it 6? Well, if you go to storage here, this data frame with 6 partitions is about 700 megabytes in memory total. And the interesting thing is each partition is 120 megs, which is the right size roughly for a partition. Remember, 50 megs to 200 megs? That's one of the reasons I use 6. Another reason I use 6 as that number is because of this. This is what our clickstream data frame looks like in memory. 720 megs, each 120 megabyte partition. So now when you're analyzing this data frame, you can basically use, you would basically use 6 tasks, right? And you'd use 3 tasks and then 3 more. So that's why it's like optimal to use 6 partitions here instead of 20. Yes?
What about 12 or 9?
12 could be fine as well, and 9 might be fine as well. Your mileage might vary. I just did 6 because it was about 100 megs for each partition. That kind of seemed fine. Yeah, in this small of a data set, going to 9 or 12 probably won't make a difference, but yeah. Okay, let's just see how long it's taking to scan this in memory. 1/3 of a second, that's pretty good. And then just to give it a cleaner name, this is kind of long to type, let's just call it clickstream DF2. Okay, there we go, clickstream DF2. And we'll stop here for a little bit and take a quick break, and then we'll come back and wrap up this lab. So let's take, let me put 15 minutes on the timer. And we will just resume in 15 minutes. So that's exactly 2:20 p.m. We'll come back and spend like 15 or 20 minutes and finish up this lab. I'm expecting to cover maybe whatever I can cover in like the next 15 minutes, and then we're going to just move into some other topic. I might just point out a few things here, and then I want to kind of move into most likely GraphX next. But let's just kind of play around with this data a little bit, and then maybe we'll do like a troubleshooting and debugging exercise, and then we'll move into another data set as well. Okay, so just to, let's go and start getting comfortable with this data, because we're going to revisit this data when we look at it through the lens of GraphFrames. Okay, so this is the first question we're going to answer. How much traffic did Google send the Apache Spark article in February 2015? So this is pretty simple. We're going to take our clickstream data frame, filter it for where the previous title is Google, other Google, and the current title is Apache Spark. And then just show the results, and that should really just show one record. So you can see that Google sent the Apache Spark article 14,000 visits, basically, in February 2015. We can also, for example, change this to Hadoop, and it's 79,000. How many unique articles did Google send traffic to? So let's do a filter on previous title, other Google. So we're going to get rid of any row. If the previous title is not other Google, get rid of it. So we keep only other Google and then do a count. So Google sent traffic to 2.5 million articles out of the roughly 5 million. What were the top 10 requested articles from Wikipedia? Take the data frame, group it by the current title. So not the previous title, but the current title. Do a sum, limit 10. Let's start by doing that. So, okay. So we're almost at the answer we want. Look, the answer we actually want is what are the top 10 articles requested. So this shows us that this article got this much traffic. But we need to basically do an order by as well to get the actual answer. So see if you can figure that out here in this challenge. And I'll give you the result, the answer in just a minute. So you can build upon this. So basically copy this, and then you need to put a order by in there. So do an order by after this sum. So we'll do order by. We want to order by the column for sum n in descending order. You see, like this column right here is called sum n. We want to order by that column. And in descending order, and then we should see what they are. So here we go, top 10 articles in February 2015. I guess the Academy Awards were going on back then. 50 Shades of Grey, I think this movie got released. And this was another film, so this is the most popular articles last year in February. So you can do the same query using SQL. So this is interesting. We're going to take our data frame, register it as a table named clickstream, and then we will select all from clickstream limit 6. So here we're actually running SQL queries now. So let's run that query. That's just a select all query, nothing special. But here we go. We can translate our question up here. You see the question we were answering here in the beginning was what were the top 10 articles requested from Wikipedia? And this was like the DataFrames answer for that, right? Right here, this is the DataFrames answer. We do a group by, sum, order by, and then a limit. Here's the SQL answer for the same question. So this is the same thing. And if you prefer SQL, the performance is the exact same. So you can write the query in SQL if that's what you prefer. And we should get the exact same results now. Okay, there we go. So we're selecting out the current title, the sum of the n column as top articles from this table, group by current title, order by top articles, descending limit. So what are our syntax you prefer? Yep. The %SQL is a Databricks magic function. You can still do this in Apache Spark, but instead of just %SQL at the command line in Scala, you would type in something like SQL context dot execute or something like that. There's like another way, and you wrap that in parentheses, and you put the string of the SQL query in there. It's just a few more characters you have to type.
I have a question about that.
Mm-hmm.
So what kind of data type does it output? And can you feed that into like another data frame or like a table or something?
You can. This is actually giving me back a data frame.
Okay.
So then you can collect that into a Scala object if you'd like. But yeah, it's just giving me back a data frame when you do a select query.
So is it just a pure matter of preference in terms of using
Only preference. There's nothing else. There's literally nothing else. Just whatever you like. Okay, a few more. Yes?
So which means that both the data frame API and the other API will be calling the underlying RDB.
The exact same. It goes through Catalyst Optimizer and all those different steps, and you get the exact same physical plan at the end regardless of whether you wrote data frames or SQL. Okay, let me just show you a few more SQL things. You can do describe on a table to see the column names and the data types. You can see functions available in SQL, and there's a lot, so I'm not going to go through all of these, but yeah, I'll just scroll through some of the functions available in SQL. There's a whole bunch. Okay, so who sent the most traffic to Wikipedia in February 2015 who are the top referrers. So I already wrote the code here. We'll just run this. We're just going to do a group by previous title. Feel free to dissect this code and play around with it later, you know. Okay. Google sent the most traffic. By far the most. Other empty is encrypted traffic. You can also see here something interesting. Twitter sent a lot more traffic than Facebook to Wikipedia in the month of February 15. I mean, a lot more traffic. Twitter sent almost 10 times as much traffic. So I don't know, maybe that says something about maybe the intellectual nature of the two social networks. I don't know. We'll come back to that question in a minute. But another interesting thing is basically Google is a significantly more popular search engine than Bing or Yahoo. Other empty is interesting because you know, you can do certain analysis to see which articles people, when they go there, they're doing HTTPS to hide where they're coming from. Usually it tends to be like articles about you know, security sensitive things like the Snowden leaks or NSA. If you go to those articles, there's a lot of traffic coming from encrypted traffic. So that's kind of interesting, like the patterns of which pages are getting the most encrypted traffic requests, or HTTPS requests, I should say. This is the only article that shows up here. Everything else is a search engine or other, basically. Okay. This is the same thing, basically, except we're going to visualize the data that comes back. So we're wrapping everything in display. And then you usually get a table back, but you can just click on the bar graph, and then you can just see very clearly Google sends the most traffic, and then encrypted traffic is the next largest sender of traffic to Wikipedia. Okay, let's keep moving. Here we're just doing a sum on the n column, and it says 3.2 billion requests total is how much we got. So remember I said in the very beginning that we have 3.2 billion requests? This is just summing up the n column, and you get 3.2 billion. That's what we just did here, sum the n column. Okay, what percentage of traffic to Wikipedia came from other English Wikipedia pages? So Google sent 1.5 billion clicks. We have a total of 3.2 billion clicks here. How much traffic came from Wikipedia itself? So for lack of time, I'm just going to go and give you this answer. It's relatively simple, and the answer is in the solutions guide. This is all you need to do. Filter out all these others. Except if you filter out all these others, then what remains in the previous title is just articles, article titles. And then just do a sum of n on that, and then we should get the results. 1.1 billion. Right? If you get rid of Google and Twitter traffic and Yahoo traffic, you get about 1.1 billion. So basically, internal clicks within Wikipedia from one page to another sent about 1.1 billion clicks. So basically, Google sent more traffic to Wikipedia than Wikipedia sent to Wikipedia. Google's pretty popular. Remember we thought Twitter was interesting because it was intellectual. It sent a lot of traffic to Wikipedia. What were the 5 top trending articles that Twitter sent traffic to? So see if you can figure this out. I'll give you a minute for this. Start with the clickstream data frame. Start with this. And then you want to basically do some sort of filter here to keep just Twitter traffic. Start with that. After that, you're going to want to do like a group by the current title. Try something like that, and then see if you can figure the rest of it out. Next, you're probably going to want to do a sum, and then I'll leave the rest to you to see if you can get this. So you might need to refer back to some of the code from above to remember how to do the syntax. If you're still trying to get it, here's the answer. Do a filter like that to keep just the Twitter traffic, group by the current title, do a sum, and then order by in descending order. So let's see what traffic Twitter sent. Okay, so much for the intellectual nature of Twitter, right? Johnny Knoxville is, by the way, the guy from the reality show Jackass. So it's not sending intellectual traffic necessarily. Actually, we can look at what Facebook is sending as well. So on Facebook in February 2015, what's this? The most popular article that Facebook sent requests to was this one, a phenomenon of human visual perception. So that's actually kind of intellectual. So maybe we shouldn't knock Facebook. I'm kind of curious now. Let's see what Yahoo sent traffic to. Okay, this is an older population, right? Still uses Yahoo, so. Wow, this is a really messed up thing. People searched Yahoo for Google, and then they went to the Wikipedia page for Google instead of just going straight to the search engine google.com. That's pretty bad. Okay. All right. This next one, let me just show you the SQL query here. This is nothing really special. This is just, you can do the same thing using SQL if you want. You can read through that if you're interested. Same results. All right, this one is basically doing red link analysis, and I'm going to skip through this for sake of time. This is basically trying to figure out which articles in Wikipedia people were trying to go to that didn't exist. So I'm just going to skip this for sake of time. Instead, let's go to question 8. Yep.
So in SQL query, how do you assign that to a variable in Scala? So we have that same SQL.
To do something like that, you would need to actually do this the other way, which is, yeah, you would do something like that, and then you would do like val, x data frame, and I forget the query, but it's something like SQL context dot like execute or something. What was it like that? Yeah, it's something like this. Maybe I'm missing the. Around, oh, yeah, so. Oops. Yeah, something like this, and that should work. And then the results of a SQL query are basically just data frames. Okay, there you go. So you get a data frame. So you have this x data frame dot show. That's all it is. Okay, we'll skip this. We'll do question 8, and I want to fly through the rest of the section so I can get into something interesting. What does the traffic inflow outflow look like for the most requested pages? Right now, there's a bunch of boilerplate code we're going to run. I'm not going to cover the code right now. I just want you to get the intuition of what I'm going to do, and then we're just going to move into something else, because there's like 2 interesting things I want to show you. I want to show you a Google visualization, and then I want to do some debugging, and then we're going to move on. So if you want to understand traffic inflow outflow patterns, okay? So just like run these cells, we're going to get page views per article data frame. This is the number of page views per article. So like this article got this many incoming requests. And now we can do link clicks per article. This means that from this article, this is how many people clicked outward. So from like this grafting article, people clicked on a link inside that article 1,500 times, right? Now we can join these two data frames and get this in-out data frame. And let me just show you 10 results in this joined data frame. So this just is interesting. I mean, we can see that in the 50 Shades of Grey article, this many people came into the article, this many people clicked out of the article, but these numbers are hard to read. Let me make a new derived column called ratio that just divides this by that, and then I might be able to interpret these answers better. And also, this is the same data in the previous and current title, so let me drop one of those. So that's what I'm basically doing here. Look, I'm taking that data frame up there, and I'm making a new column, a derived column. I'm going to call this new column ratio, and all it's doing is just dividing the out count by the in count, and then I'm just caching this data frame. And then I'm just selecting out the current title. There's the in, out, and ratio. Okay, so let's see if we can interpret these results for a few seconds. Okay, so 50 Shades of Grey, 50% of the people who come to this page click on a link and continue onward. For the Academy Awards, 65% of people who come to the Academy Awards page seem to like click on a link. But look at the Alive page. The Alive page is killing traffic. I mean, 220,000 clicks, more actually, 2.2 million clicks came in, but only 3,000 clicks came out of the Alive page. So what is going on with this Alive page? Nobody stays on Wikipedia when they land here. Okay, Alive may refer to live publications, films, music, and a whole bunch of albums and songs. Yeah, pretty much if this is what I had to see, I would click back and do a better Google search, right? So that's what we're seeing here. That's why the ratio here is 0. Let's make a diagram for using Google Charts. This is the third visualization library I'm going to show you. We looked at Databricks visualization. We looked at Matplotlib. Later I'll show you D3. But now let's look at Google visualizations and how to incorporate that. I'm going to try to make a sand key diagram for the Apache Spark page. So we're going to, from the in-out ratio data frame, we're going to focus on just the Apache Spark page, which has a ratio of about 18% of clicks continuing onward. So this is a SQL query. We don't need to run that. So this is showing us where traffic to the Apache Spark page comes from. Google sent 14,000 hits to Apache Spark. Encrypted traffic was 1,500. Hadoop sent 709 clicks to Apache Spark. So this is basically the different pages or search engines or whatever that send traffic to Apache Spark sorted by the N column. Let's do the same thing, but if under the previous title, let's put Apache Spark here and see which articles the Apache Spark page is sending traffic onward to. See if you can figure that out. So if the previous title is Apache Spark, where is Apache Spark sending traffic onward to? This is going to look a lot like this query, but we're going to change this to previous title, right? Let me copy this from up there. And let me just change current title to previous title. There we go. Okay, so Apache Spark. From Apache Spark, people go to Hadoop 800 times. Matei Zaharia, the creator of Apache Spark's page, 600 times. This is hard to interpret though because it's just numeric table with rows and columns. We can actually make a sand key diagram out of this by using display HTML and using the the Google visualization library to do this. So let me just run this cell so you can see the results. There we go. Now we have a Sankey diagram showing the same results. So this is showing us that Google sent 14,000 clicks to Apache Spark. Hadoop sent 901 clicks to Apache Spark. When people come to the Apache Spark page, most people don't click onward. But for the, for like the roughly, it looks like maybe 15 or 20% of people who click onward, most people go to the Apache Hadoop page. The second most frequented page is Matei's page, followed by Mesos, 322. So this is a cool way to visualize the data for the clickstream. Okay, one last thing. Catalyst Optimizer. And then I have a quick demo for you. In the Catalyst Optimizer, you can run explain on a data frame to basically see the physical plan here, or you can run explain true to actually see all the different plans. That's really all I had there. Let's do this post-lab demo. So the way this demo works is, this is the question we want to answer, and imagine that here you inherited this code from your colleague, and he's like telling you, hey, it's not working. Help me fix it. So this is a data analyst's notebook. So maybe a data analyst wrote this code, and now we have to put our data engineering hat back on and try to do some troubleshooting based on what we learned in the last notebook for the data engineer. Remember we were looking at the Spark UI and everything? Let's see if you can figure this out. This is going to be a little challenging, but it's a pretty short demo. We want to find out which pages multiplied the input clicks the most. So think about what this means. This means that which pages brought the most traffic to other Wikipedia pages. So we want to know when somebody goes to this specific page, almost everyone clicks onward. That's what we want to understand. What are those pages? Okay, so we're just going to keep hitting Shift Enter. Ignore some of, don't worry too much about understanding the code. We're just going to hit Shift Enter and then get to the cell that doesn't work. Okay? So first we're going to start with this data frame. We're going to make the input in clicks data frame. This is the amount of clicks coming into each page. It's kind of similar to what we did earlier. This is in clicks. So this is going to, when you see allo allo, it means the allo allo article got 17,000 incoming clicks. This is out clicks data frame. Okay, this is out clicks data frame. Very similar, like I said, to what we were looking at before. Okay, this is out clicks. This means that this article here, people, when they got to that article, about 400 times they clicked onward. Then we're going to do this. We're going to make a user-defined function called compare UDF that takes in two strings and it lowercases both of the strings, title 1 and title 2, gets lowercased, and then we just check to see if they're the same. Pretty simple, right? Just a simple UDF to lowercase and check if the two titles are the same. And then we're doing a join. Joined UDF means we take the output clicks, join it on the input clicks on this compare UDF. With compare UDF, we're sending it from the input clicks the current title, from the output clicks the previous title, and we're just doing a join. Let's run this and see what happens. Wait, I need to run the compare UDF first. Okay, I'm going to run this. And basically what this is going to happen is this cell is not going to run. It's going to take forever. It's not going to complete. So the very first step in understanding why this is going to happen is to expand this. And notice that this order by is basically kicking off, this is kicking off a job. Do you see what's going on here? What sticks out at you? 40,000 tasks. So see if you can figure out why. See if you can troubleshoot this. I'll give you a minute, and if you know what's going on, just kind of yell out the answer. So you already kind of know what to do. I've shown you how to troubleshoot this, but it's just a matter of synthesizing the stuff you've learned so far. anybody know? I still don't hear the right answer. Try looking at the Spark user interface. That's exactly right. So let's look at how you figured that out. I'm going to go to the Spark user interface. This is running job 42, correct? So I need to hone in on job 42. So I'll go to the Spark user interface. This was a data frame or SQL type of query. So I'm going to go to the SQL tab. And I'm looking for, job 42. This is job 42. It's currently running. It's been running for 2 minutes. Let's take a look at its visualization. It's reading from memory here. It's reading from memory there as well. So it's reading 2 data frames from memory. It's doing a filter there, and this filter is getting rid of half the data. That's pretty good. There's some aggregations going on both sides. This is a shuffle. On both sides, there's 2 shuffles going on. Here we go, Cartesian product. If you know about SQL, these are to be avoided. This is basically taking the 5,200 rows from this side, the left side, and joining it to the 82 million rows on the right side to make an insane explosion of data. It's basically taking every row on the left and joining it to every row on the right. Cartesian products are not efficient to run. So the reason this is happening is we should stop this and cancel this, by the way. The reason this is happening, does anybody know? Yeah, the problem is this UDF. UDFs are opaque to Spark's SQL. Like Spark can't do any optimizations inside the UDF. It runs them in a really kind of naive way. So we want to not do our equality check in the UDF. Remember the triple equals that we learned about to look for 2 columns? That's one of the built-in Spark SQL functions. And there's about 500 or 600 of them. You always want to try to use the built-in Spark SQL functions like these. Okay, there's a lot of them here. I think there's at least 600. Don't write a UDF if you can use a built-in Spark SQL function, because Spark can do optimizations here that I can't do with your UDF. Let me show you how we would fix this. What I'm going to do is, instead of making a compare UDF, I'm going to make a format UDF. And my format UDF, all it's going to do is it's going to take a title that's a string and take the title and just lowercase it to lowercase. This is not a costly operation. That's going to be my only UDF, format UDF, okay? And then I'm not going to use my compare UDF anymore. Instead, let me delete this. I don't want to do the equality check like this. I want to actually use the triple equals to do it. And I'm going to just use format UDF only to do the lowercasing. So let's do format UDF on the out.previous title. And then on the other side, I'll also use format UDF just to lowercase the in current title. There we go. That's all I need to do to fix this. The trick here is now I'm not using a UDF to do a quality check. I'm only using a UDF for something trivial to do a lowercase. And then let me run this cell. So now it's running. Let's take a look at the execution of how this is running now. Okay, there you go. Notice that, okay, I should have changed that setting from 200 to 3 as well, or 6. But that stage with 40,000 tasks is gone, right? And it's actually looking like it's going to complete. Let's go back to the Spark user interface while this is running. This is job 43, right? Let's look at what happened with job 43. We had a Cartesian product before in job 42, but now job 43 is running. And if I scroll down now, I can see that the Cartesian join has been replaced by a more efficient sort merge join. Let's look at the results. Okay, so this is where the multiplier effect is the greatest. 11 input clicks. How would you get 500,000 output clicks out of that? That's kind of odd. Maybe I would troubleshoot that a little bit, but by looking at the results in general, what I'm seeing here is a lot of movies and TV series. Salman Khan is like a Bollywood actor. So I guess my implication here is that when you are looking at these type of articles on Wikipedia, you probably have a lot of time to kill. Right? You're clicking onward in a lot of other articles. Okay, so there's another film right there. Broadway theater. Okay, let's do the opposite. What I'm going to do is just change the descending here and get rid of that. Let's see which articles are killing traffic to Wikipedia. So these are bubbling up traffic to Wikipedia. These movies, people go to there and then they're like clicking on a bunch of links in these articles. But what are the articles where when people get there, they're not clicking onward? Let's see. Let's see if you can see a pattern. Okay, wow. Integral got 44 million incoming clicks and like 14 out clicks. I'm kind of suspicious of that. That seems insanely low. So I would have to troubleshoot my math a little bit, or my code a little bit. But in general, look at these type of articles. These are all like scientific things, right? Like watt, petra, ultraviolet, gamma, proton, space. So people come to these articles and they don't really click onward that much. I mean, it kind of makes sense if you think about it. If you think about integral, I mean, people who are mathematicians might simply be, bookmarking this article and they just like quickly go there to refer to some equation, and then they just refer to something and then they leave, right? So it kind of makes sense if you think about what's going on. Okay. So that's it for clickstream. Let's see, any questions about what we covered so far? No? Let's see how we're doing on time. I want to, let's see, what I want to do next is, I think what I'm going to do is actually jump into Graph, because that's the same clickstream data. I'm going to spend about 15-20 minutes on Graph, but I'm going to do Graph a specific way. I'm not going to do this like a normal notebook. I'm just going to fly through it as just a README notebook, like a demo, because there was kind of less interest here in going deep into Graph. So I'm going to do Graph really quickly in like 15-20 minutes. And then what I'm going to do is I'm going to also do the same thing with this one. How many people here have used datasets before? The new API. Okay, well, I'm going to kind of tell you a few things about datasets, but I'm not going to cover this notebook in depth. Okay? And then what we'll do is we'll take a short break. Then when we come back, we'll do machine learning and streaming. Okay, remember, I'm not intending to cover all the material here. I just want to give you a taste of some of this stuff. So let's do Graph really quickly. Now notice, even if you go to the Run Me version here and go to Graph, even if you do that, this is going to just be the README version. So all the cells are already executed. Actually, before we do this, let's go look at this Graph D3 notebook really quick. We'll spend only 1 minute here. If I scroll all the way down and go to bonus graph d3.js and click on that, we're not going to run this. I'm just going to show you the results. This is a Python notebook. This is a demo that Michael Armburst, one of the main engineers of Spark SQL, he did a demo at Spark Summit East in New York City. And if you go to just YouTube and find Michael's demo from Spark Summit East, he's basically looking at the clickstream data, and then he's looking at refers to the Donald Trump page, and then he's loading the D3 library, And I just want to show you the visualization, really. I'm just going to scroll down. And right here, I just want to show you this. He basically has two data frames. He has a data frame for Donald Trump and a data frame for Bernie Sanders and one for Hillary Clinton and one for Ted Cruz. And then he's basically making this visualization. You can see this is Hillary Clinton, and you can see all of the articles around her. And you can see that she is connected to the Democratic Party presidential candidates page. On the left here, we have Donald Trump and the different articles for him. And we can see that he's connected to United States presidential election. So is Bernie Sanders. So is Ted Cruz. And so is Hillary Clinton. They're all connected to this vertex here. And then there's another one that somebody made here for Apache Spark, Hadoop, Cassandra, and Tomcat, all these Apache pages. So this is just for you to play around with later. I'm not going to cover this much in depth, but you can play around with this. Okay. What I really want to actually cover is a little bit about graph processing. How many people here know like the fundamentals of graph processing? So you kind of have played hands-on with some graph engine like Giraffe or Neo4j. Just raise your hand if you have. Okay, so if you haven't done this, the whole motivation around this next 15 minutes is simply to convince you that sometimes it really makes sense to look at your data from a graph perspective. We just spent like 30 minutes looking at clickstream through the perspective of rows and columns, but there are certain insights that we would never be able to pull out of the clickstream data if we limited ourselves to data frames and SQL queries. That's what I want to show you here. What we're going to do with the clickstream data is we're going to run PageRank on it, and we're going to run the shortest path algorithm on it. These two things are too computationally expensive to do from DataFrames or SQL, so we're going to have to use a graph library to do this. Basically, the way to do this in Databricks is, notice here under Library, the GraphFrames library is already imported. But if you were on your own community edition, how would you import that? Well, you basically, don't do any of this. Right now, for 15 minutes, just you're in demo state, right? So just kind of watch what I'm doing. We're going to fly through graph. Then we're going to fly through data sets really quickly. Then we'll take a break and come back and do machine learning and streaming hands-on. Okay, here's how you import data, like a library. Go to Create, Library. And then we're going to change from Java to a Maven coordinate. And here, we're just going to type in GraphFrames and then search. What's that? Let's see, that might take a minute. Or oh, did I? Sorry. Okay, that's never going to come back. Oh, yep, I definitely had a typo there. Thank you. GraphFrames. How do I know GraphFrames library even exists? How many people here have used Spark packages? Does anybody know what this is? Spark packages is a collection of third-party libraries for Spark. You might have heard of GraphX. GraphX is the RDD implementation of the Graph library. GraphFrames is the new data frame implementation of Graph library. If you go to Spark packages, here you can see that there are basically many different libraries for Spark. This stuff is not part of the Spark source code. If you go to like Graph here, by the way, you can see all these like Graph libraries you can use. These are third-party libraries for Spark. There's GraphFrames. You can click on it. And this is how you can import these libraries from the normal Scala shell for Spark. It's still pretty easy to do. For example, maybe you want to read XML data, okay? You can't do that out of the box with Spark SQL or DataFrames. It doesn't support reading XML data. However, if you go to data sources here, and then if you just kind of look at all these connectors, Avro, Redshift, there's an XML connector here. Let me find it by just searching for XML. There it is. So you can just basically now import this XML package, and then you can read an XML file. There's a whole bunch of machine learning packages as well that are not part of the Spark source code. Here's machine learning. Also, if you create a cool library that your company is going to allow you to open source, then please add that here so the rest of the community can benefit. So here, what we're doing is we're just bringing in the GraphFrames package. This is it right here, GraphFrames. This is the version. I want it for Spark 1.6. I'm going to hit select, and then I can just hit create library. And if I do that, then it will just show up here as GraphFrames. That's all you have to do. After that, let me go back into the GraphFrames lab. So I'll go to Run Me, Graph, and we're just going to fly through this like a README version of this. Okay, I'm not going to even bother attaching it to the cluster. Okay, so let's learn graph fundamentals. Okay, now graphs are made of vertices and edges. Every article in our clickstream data is just going to become a vertex. Here's the Apache Spark vertex. Here's the Apache Hadoop article. And there's a connection because somebody maybe clicked from Apache Spark into Apache Hadoop. More specifically, you have to give the vertices long data types. So the vertex ID is going to be the article ID. Remember we got rid of this earlier? Now we're not going to get rid of it because we need to give the vertex in GraphFrames a long data type. So we're going to keep that long number that we had gotten rid of before. So this is the article ID. This is the article ID for Hadoop. And in the edge, we might put a label like 808. That means that 800, this is N, right? The N column. 808 times people clicked from Apache Spark to Hadoop. This is fundamentals of graph processing, but how do you actually make a graph frame? You basically take a vertex data frame like this that has the vertex ID and then the article title. We need to first get a data frame like this. That's the vertices data frame. Here's the edges data frame that has a source article and a destination article. And everything else is just metadata. You really just need these two things. Here, under vertices, you really just need the ID column. And you can put like 20 different metadata things if you want. ID title is just metadata. Here, type and N are just metadata on the edge. You just take these two data frames and you combine them into a graph frame, and then you can do graph operations like PageRank or shortest path. Let me show you. Here is my vertices data frame. I created the vertices data frame here in this ETL notebook for here. You can go into there and look at how I made it. So you can kind of skim through this. This is how I made the vertices data frame. And then I just wrote it to S3. You can go through this on your own time. Here's how I made the edges data frame. And then I just wrote it to S3. And they were just like picking it up in the next notebook. So let me go back to that notebook. So let me just show you what the vertices data frame looks like. Here it is. Okay? That's the vertices data frame. Here, and there's, by the way, there's 3 million vertices in our graph. Here's the edges data frame, and that's what it looks like. Source and destination. And then all of this stuff is just metadata. How many edges are there? 22 million. Okay, we take this edges data frame and the other data frame, the vertices data frame, and then this is how you combine it into a graph. You make a clickstream graph. You just give it the 2 data frames. I mean, it's dead simple. And now we have a graph. So now you can start thinking about the data like this. We have this graph with 3 million vertices. This is a small subgraph here. Apache Spark sent traffic to Hadoop and Mate and Apache Mesos. But also articles and search engines send traffic to Spark, right? So really it's like this. Google sent 14,000 hits to Apache Spark. This is encrypted traffic, 1,500, and this is Hadoop. Actually, this doesn't look right. We have Hadoop there and we have Hadoop there. We need to collapse Hadoop into just one vertex. So really, it should look like this. Hadoop actually has 2 unidirectional edges. There's one edge going from Hadoop to Apache Spark because Hadoop sent 901 hits to Apache Spark, and Spark sent 808 hits to Apache Hadoop. So now imagine this with 3 million vertices, and that's really what our graph looks like. Graphs are everywhere. Let me just give you a few examples of where graphs exist in Wikipedia. There's a Wikipedians to edits graph. Now imagine in this hypothetical scenario, in this diagram, we're looking at 4 different articles. The Summer Olympics article for 2016, the new Boeing 777X jet that's coming out, I think, in the next few years, Academy Awards, and CRISPR, the DNA gene editing technology. And if you look at the editor to article, maybe a bunch of athletes edit the Summer Olympics article, and here a bunch of pilots, I guess, commercial and airline and military pilots are editing the new Boeing article, and scientists and doctors are editing CRISPR, and musicians and actors are editing Academy Awards, and maybe this female pizza delivery woman is very intellectual and is editing all of them. You could make a graph like this, is the point. This data, though, is 13 terabytes. However, Spark is capable of looking at that data and making a massive graph of a connection from editor, which editor is going to be either an anonymous IP address or a logged in Wikipedia username, IP address or logged in username, connected to the article itself, right? So unidirectional edge like that. So imagine that is one graph you could make. You can make a graph like this of looking at the English Wikipedia 54 gigabyte snapshot, just English Wikipedia, not anything to do with editors. And then, for example, for the Apache Spark article, in that article, there's all these links. So from Apache Spark Vertex, you make a unidirectional edge to every other article in Wikipedia where there's a link in Apache Spark. And then, like under the data structure article, there's furthermore many different links in that article, right? So you can make this link graph for Wikipedia as well. Can you guys guess what this graph shows?
LinkedIn connection?
It's not a LinkedIn connection. This is actually a real graph that was released by the Wikimedia Foundation about 4 months ago. This is something really interesting, actually. What we're seeing here is a real image released by the Wikimedia Foundation following an investigation called Orange Moody. The Wikimedia Foundation identified 381 malicious Wikipedia editors and IP accounts who were creating promotional articles, inserting promotional links into Wikipedia, and doing disruptive edits for profit. So what we're looking at here is the yellow bubbles are anonymous IPs. The green bubbles are logged in Wikipedia users. So let me explain. See this green bubble here? This is a logged in Wikipedia username. And what this means is that this logged in username edited the same collection of articles as these anonymous IP addresses. These are all yellow. That's why they're anonymous. So what we have here is basically a sock puppet network. That was probably controlled by no more than maybe 2 or 3 people. The theory goes that these were people probably in India. And what they were doing is malicious things in Wikipedia. For example, one thing they were doing is pretty stupid. What they were doing is they would go to like a famous person's page in Wikipedia and they would delete it. And then they would contact that famous person and request like bitcoins to restore their page. Now, that is a pretty stupid attack because Wikimedia Foundation it's logged, so they can see who deleted that page. So they basically just put that in a table to say this anonymous IP address deleted that page, and then they'll just restore that page. A week later, somebody else complains, hey, somebody deleted my article and wants Bitcoin. And that's maybe a logged in user who deleted that page. So you add that to the same table, right? So that happens like 10 times. And now you have like 5 anonymous IP addresses and 5 logged in usernames maybe that you got some complaints about. And these 10 users were in the log the ones who deleted articles, right? Then what you do is you try to figure out these 10 accounts, what are the pages that these 10 accounts edited, and where is the overlap? So you then find like these 10 accounts edited maybe these 50 pages, these 50 articles. And then you try to extract from that what are the other users who also did edits to a majority of those 50 pages. Based on that, you can extrapolate out a bunch of users who collaborated with those 10 users. So what we're seeing here, for example, is that this is like a bigger green circle because this means that this circle did a bunch of edits to Wikipedia. This logged in user actually did probably some proper edits. But this logged in green user edited similar articles to these anonymous IP addresses that probably came from a VPN. So what we're seeing here is collaboration among these anonymous IP addresses in yellow and the logged in users in green. So this is basically the sock puppet network. And the theory is that there are probably a bunch of these in Wikipedia. A lot of these sock puppet networks, some that have not been uncovered yet. All right, so this is analysis that you can do only from a graph perspective, right? So all of these accounts were banned from Wikipedia. Okay, I want to really quickly cover, I'm going to skip this in count and out degree stuff. What I really just want to jump down to is like PageRank and show you some of the graph algorithms. I just want to show you how easy it is to run PageRank and shortest path. What we're doing here, by the way, is we're extracting out a subgraph from our clickstream graph. We're extracting out a subgraph. What we're doing is we're removing the main page because we're going to do shortest path in just a minute. And if you do shortest path from this article to that article, the shortest path is always going to be from this article to the main page to that article. All right, so we're just going to get rid of the main page then we'll do shortest path. So we're extracting out a subgraph here where we have all the same vertices and edges, except we're getting rid of the main page. Okay, so now we basically have a subgraph. Another thing I'm doing here is I'm actually just keeping only edges greater than n equals 300. You have to do this to reduce the data set to actually let these commands complete on Community Edition in Databricks. This is a local tiny cluster, so I'm just reducing the data in an intelligent way. Okay, so I'm basically just creating a subgraph here. And then I have basically a subgraph. I'm also getting rid of all of these others. So I'm getting rid of Google and Wikipedia traffic and Bing traffic because I only want Wikipedia articles in my subgraph. Okay, so here's my subgraph. Basically, I just did two things. I got rid of main page. I got rid of all the search engines and those things. All the other. Shortest path. What is the fastest way to get from Apache Spark to Kevin Bacon? I figured that would be fun to do. To do this, we need to first, from our clickstream graph or from the subgraph, we need to get the ID for Apache Spark, the article ID. So here's the article ID for Apache Spark. Here's the article ID for Kevin Bacon. And then all we need to do is notice from Apache Spark, you can go outward 29 times. There's 29 articles you can click on to continue out of Apache Spark. Coming into Kevin Bacon, there's 170 articles that link into Kevin Bacon. So this is how many paths you can take to come into Kevin Bacon. And anyway, this is the shortest path algorithm. It takes about 8 minutes to run in Databricks. This is running on the subgraph where n is greater than 300 and there's no main page. All you do is you give the original article for Apache Spark. This is Kevin Bacon. You say run. Then you get the shortest path data frame. And on the shortest path data frame, I'm just caching it. And I get 63 results. That means there's 63 results that give you 4 hops. Let's look at one of them. What I'm going to do here is I'm just going to expand these. So from Apache Spark, you could go to Apache Hadoop. From Spark, you could go to Hadoop. And then this is the next vertex. So from Spark, you go to Hadoop. And then this is an edge. Okay, so from Spark, you go to Hadoop. From Hadoop, you go to Amazon.com. This is a vertex. I'll just expand the edges instead. Okay, so Spark to Hadoop to Amazon to Google search. Oops. Okay, after Google search, you'd go to Kevin Bacon. So that's like, what, 4 hops or something. There's other ways to do it as well. So you don't have to come from Google search. You can also come from the wiki article. You can also come from, I don't know what that is, but that article. So there's like 63 ways you can do just 4 hops to get from one page to the other. So I just wanted to kind of show you how to do that. Another thing I wanted to show you really quickly is PageRank, and this is really simple to run. On clickstream graph, we're just going to do PageRank, max iterations 3, and this takes like 13 minutes to run on Databricks Community Edition. We get a PageRank graph back. In the PageRank graph on vertices, this is where we have a new column has been added to the vertices data frame, and it just gives us the PageRank number. We can sort this. We can do order by PageRank like this. Order by PageRank in descending order. And now we're basically seeing what are the most influential pages in Wikipedia according to the PageRank algorithm. The main page first. And then we're seeing the Internet Movie Database article is really important. And then United States, Order of the British Empire, India, United Kingdom, YouTube, Alexa, Internet, and World War II. China, Canada, Germany. These are the most influential pages in Wikipedia. Now, this is based on clickstream, right? It would be different if you actually extracted out the link graph from English Wikipedia and then you ran PageRank. Maybe you would get some different results. This is trying to figure out from the clickstream perspective what are the most influential articles. Okay. That's really it for graph. What I want to do next is I want to really quickly say a few things about data sets. I'm not going to cover this lab. This is just consider this is like homework assignment or something for you to do in your own time. I'm just going to tell you what's in here in like 5 minutes, and we'll take a break. And then when we come back, we'll get into machine learning and natural language processing and streaming. Okay. Let me just cover what's in here. You know what I'm going to do is I'm going to jump to the README version of this notebook for data sets. And I'm just going to tell you like a few important critical things about data sets. Let me see. There's a slide I want to load up. This one. Okay, so data sets are a little bit similar to RDDs. The API for data sets looks like the RDD API, but the main difference for this is that basically, data frames let you work on your data in kind of like an object-oriented way. RDDs let you work on your data in a functional way. Data sets give you the best of both worlds. Data sets let you work on the data in a functional way, but data sets basically give you type safety. When you use data frames, you lose type safety. That's the most important thing to understand. Actually, I have one more slide that could be really important here. Hang on. Where is it? Give me 1 second. Ooh, okay, I don't know where it is. Okay, well, I can't find that specific slide. But, okay, the high-level idea here is that if you really like the functional API of RDDs, then you will really like data sets because it lets you use a very similar API, but it has type safety. What that basically means is you have compile time type safety with data sets. If you do something incorrect with a column where like you think a column has string data, but it's really integer data, then you'll get an error right away. and you won't have to wait till runtime to see that error with data sets. Let me show you this specific notebook. Basically, what you'll do if you do this notebook later as homework is we're going to answer these 3 questions looking at the page count data. Remember, like the hourly file? We're going to look at the hourly file, answer these 3 questions, but essentially what you do in this lab is you write the same answer using RDDs, and then you write the same answer using data sets and then data frames. So you're going to see 3 different ways to write code, and then you're going to look at performance differences between the 3 techniques, and you'll also look at like memory consumption differences based on, like, if you read some data from disk and load it up into an RDD in memory, how much memory does it take when you're using an RDD that's deserialized or serialized, versus if you read the exact same data and bring it up into memory as a data frame, as a tungsten binary data object, how much memory does it take in memory? How much room does it take in memory? So that's the kind of stuff that you're exploring here. This is kind of like an advanced lab, I would say. But basically, if you want to see the difference between RDDs and data sets, then this is going to be pretty cool. Another important thing you should know is that if you use data sets and data frames, then both of them store the data in memory using the tungsten binary object. So this is really interesting. So you can basically load the data from disk into tungsten binary format and then look at the data using data sets or data frames. And it's going to just look at the same data. Data sets and data frames operate on tungsten binary object. However, here's where it gets tricky. If you take that data frame and then convert it to an RDD and then do something with it, it's going to be really costly. And this is one of the most important takeaways from this lab, that if you take a tungsten binary object and then convert the data frame to an RDD, then you're pivoting the data from a columnar representation to a row representation, and that's quite costly. So going from tungsten binary format to RDD, and then from RDD back to like a data frame or a data set is very costly. However, if you just stay within the data frame and data set API, then you basically are staying in the tungsten binary object world, and then it's like a really simple and a really cheap conversion, because data sets and data frames both work on tungsten binary object. Okay, those are like the main takeaways out of this lab. I'll just quickly skim through it to show you some of the stuff. What you do in this lab is you're operating on the real data. So I'm not doing any like tricks with this data. This is like the real data that you get from the Wikimedia Foundation, the hourly file. So I'm not doing any pre-processing this time. So then you basically make an RDD out of that data, page counts RDD, and then you count it. And then you basically also, you make a data set. Out of the same data, you make a data set. And then you do like the same query with data set. And then you're like caching the RDD and the data set. And you'll notice that the data set is far more efficient to store in memory because of columnar compression. And the RDD is by default, RDD.cache means deserialized in memory. And deserialized RDD takes up way more data, 700 megabytes in memory. All right, so that's one of the first takeaways here. And then you do stuff like you make a page count parsing function. I don't want to cover this in depth because it gets kind of pretty detailed, but you basically parse that RDD with your parsing function, and then you parse the data set with the parsing function as well. And then when you look at it in memory, you'll basically notice that the RDD is way more costly in memory. You basically see what you're doing is you're answering these business questions with the RDD answer, and then you're going to answer the same thing with the data set answer. Sometimes what you'll do is, in Spark 1.6, a sum function does not exist on data sets. It does in Spark 2.0. This is a Spark 1.6 lab. So in Spark 1.6, you can't do sum. So there's a few different strategies of how you can do a sum. You can collect the data and then do a Scala sum, or you can convert the data set to a data frame and then you can do a sum. That's what we're doing here. We're taking the data set, doing a map on it, which gives us back a data set, converting it to a data frame, and then doing the sum operation, because in Spark 1.6, DataFrames API has a sum operation. And finally, another trick is we write a custom aggregator for data sets. So we write a custom aggregator called ZeroSum, and then we basically use that to do a sum as well. And then we look at some performance differences here as well. And basically, that's what we're doing here. We're looking at a data set answer and a data frame answer. Okay, so that's just like really high level. I know I didn't really cover that much in depth. I just want you to know what's in there. So if you're interested in using the dataset API, you can go to that. I'll take the question in the back.
So in 2.0,
Mm-hmm.
dataset API is clustering on 30 data frames.
It's more like the dataset API will be more similar to the RDD API. However, in Spark 1.6, aggregator functions and statistics don't exist in the dataset API. So I'm doing this weird trick here. Basically, my strategies here, look, I'm doing like strategy 3 and strategy 2 and strategy 1. You don't have to do these in Spark 2.0. Some exists out of the box in Spark 2.0. Neil, yep.
Can you talk a little bit about Python and data sets? I mean, does it make any sense?
Sure, that's a good question. Actually, what I would refer you to for that is just a Spark official documentation for Spark 2.0. So I don't know if that got released yet, but it will be released tomorrow. What I can show you really quickly is the preview documentation for Spark 2.0, which does refer to something about the data. It does refer to data sets with Python. So let me just find that really quick. Give me 1 second. Okay, hang on. Okay, so what I'm looking at here is this is something kind of a neat trick. This is Patrick Wendell's page on Apache. This is Spark Nightly. From here, I can actually find the documentation to Spark 2.0. So here's the 2.0 docs for Spark. And if you really want to see this, here's like the June 6th build. I'll put a link in this in the notes document here. So notes to share with students. There we go. That's the Spark 2.0 early preview for the documentation. If I go there and I go to, this is C2.0. If I go to this guide and I go to DataFrames, now see how it talks about data sets? Here, if I scroll down to data sets, I can see some information. This is a new experimental interface for Spark 1.6, provides the benefits of RDD, so strong typing, ability to use powerful Lambda functions with the benefits of Spark SQL's optimized execution engine. Data sets have operations like map, flat map, filter. Look at this part, Neil. This should answer your question. Dataset API can be used in both Scala and Java. Python does not have support for Dataset API, but due to its dynamic nature, many of the benefits are already available. You can access the field of a row of a name like that. Full Python support will be added in a future release. So hopefully that answers your question about the Java Python API. Let's see. I want to take a break in a second, but what I want to do before I take a break is I want to mention like 2 or 3 things about Spark's Catalyst Optimizer. And I want to kind of convince you why you should not use the RDD API, okay? So I'm going to say like 2 or 3 things for like a couple of minutes, and then we can go ahead and take a break. We'll come back and do machine learning and streaming. Okay. So there's a couple of, oh, this is the slide I was looking for before. Comparison difference between Spark SQL queries, data frame queries, and data sets queries. These are the 3 APIs you want to be using in 2016. Don't use the RDD API because, one, the RDD API requires a lot of knowledge of wide transformations and narrow transformations and what's going on under the hood so you can write the RDD code properly. There are certain optimizations that don't exist in the RDD API at all. Those are the ones, I'm going to point those out in a second. those optimizations that don't exist in the RDD API, they do exist in the Spark SQL, DataFrames, and Datasets API. Because if you write code through SQL, DataFrames, or Datasets, the code will always go through the Spark SQL Catalyst optimizer. And then it will eventually generate a physical plan with code generation, and RDDs will run ultimately under the cover. However, one thing you might want to know is datasets give you compile time type safety for syntax errors and analysis errors. If you use DataFrames, you only get compile time type safety for syntax errors, but not analysis errors. SQL gives you errors only at runtime. Because of this, if you're a Scala programmer who cares a lot about type safety, you might really prefer datasets. A data set is really just a data frame of row objects. Okay, what I really want to do is actually tell you a couple of things about Catalyst and why you should actually use Catalyst. So this is Catalyst. Remember, SQL queries, data frame queries, and dataset queries go through Catalyst. If you remember, this was like the full path of Catalyst. What are some of the logical optimizations that can happen? I'm going to mention a couple of those. Here's what they are. Logical optimizations that don't happen if you use RDD API. They only happen with SQL, DataFrame, and datasets. One thing is we can push filter predicates down to the data source. We can use Parquet to skip entire blocks of data. What does this all mean? Let me just show you through this. Here are some of the optimizations that can happen with Catalyst. Now look at what we did here. Imagine that this is the code that you wrote. You wrote some code to take this data frame of events file and users file, then you did a join, and then you did a filter. Okay, this is the code that you wrote. You had a data frame, then you did a join, then you did a filter on the results. Okay, if you're using data frames to do this, what Spark's Catalyst optimizer might do is it might push the filter under the join. This is one of the logical optimizations. Look, the filter got pushed under the join so that now we are basically, maybe what the filter was doing is it's trying to do a filter to only look at the results for users over age 21. So it makes more sense to do that before the join. So we read the user's CSV file, we read the user's file, and then we do a filter initially to keep only the users over age 21. We get that subset of users, and then you can do the join, and that would be a more efficient join than actually doing the join across all of the users with all of the ages of the users. And then if you do the filter, this is a more expensive join. So this is one of the optimizations that the Catalyst optimizer will do automatically. If you write the code like this to do the filter after the join, the way it might actually run would look like this with the physical plan. Right, this is a big win for speed. Now, you can take this one step further. You see, like, if this was JSON over here, then this is the most optimization you can do. However, if the underlying data source is something like Parquet or a relational database or Cassandra, certain of these optimized data sources let you take this trick one step further. Notice here, if you were reading from a Parquet file, we can push the filter down into the Parquet file. So what we're doing now is Spark SQL is basically only reading the rows where the column is greater than 21. So what we can do with like Cassandra or JDBC or Parquet is, for example, with like relational databases, we can push the filter into the relational database itself with like a where clause. And we tell the relational database, or like Cassandra, give me back the rows where the users are over age 21. And the relational database or Cassandra will only give you back that subset of users. So now there's no filter taking place in Spark at all. You've pushed that down into the data source. Also, that's called predicate pushdown. Column pruning, what that means is if you're, once again, if you're reading from like Parquet or Cassandra or a relational database, I think HBase supports this now as well, then what you can do is if for every row you have 10,000 columns, with column pruning, what Spark can do is if you only are doing your analysis that needs 5 columns out of 10,000, then we'll only request 5 columns out of the relational database or Cassandra or like the Parquet file. So now you're reading only some subset of rows and only some subset of columns, and then you're doing your analysis in Spark. So this is called column pruning, where you only read a few of the columns. So these things are not possible if the underlying data source is HDFS or CSV or JSON. Because in HDFS, there's no way you can tell HDFS, just give me back the data where the users are over age 21. With HDFS, you have to read all of the data into Spark. Then you have to do the filter within Spark. If it's CSV or JSON, you still have to read all the data into Spark, then do the filter within Spark. Right? So you really want to try to use this optimized data format like Parquet, or a database like a NoSQL database that supports predicate pushdown and column pruning like Cassandra or relational databases. There's an example of predicate pushdown against a relational database. If you write code like this in Spark, look at the very end, we're just doing a where clause with name equals Michael. So what we're doing here is we're reading from our Postgres database, and then it looks like we're loading all the data in, and then we're doing a where. That's what it looks like. But what really happens is Spark will send this to Postgres. Select all from people where name equals Michael. We've pushed the filter down into Postgres. That's one cool thing about the Catalyst optimizer. Another thing, you already saw this one, efficient joins. If you do a join, this is making a UDF where we're doing a join within the UDF. This is going to give you a Cartesian join. However, if you do a join using DataFrames, here we're getting a sort merge join. So what this is saying is basically don't use UDFs. Use the built-in functions in Spark SQL, because they will let the Spark Catalyst optimizer do certain optimizations that you can't do when you use a UDF. If you're using this, if you're doing this with RDDs, that would also be very, very costly, because you're bypassing the Catalyst optimizer completely. RDDs don't go through Catalyst at all. Only SQL, DataFrames, and datasets. Okay, that's like the main point I basically wanted to make to convince you to use RDDs. I'm sorry, to not use RDDs. Complete opposite. If that 10-minute convinced you to use RDDs, then I basically failed. That's not what I wanted to do at all. Okay, that's really it for now. Let's take like a short 10 or 15-minute break. Actually, what I'm going to do is I'll put a timer here to resume at, let's just do 15 minutes. Okay, so we'll resume in exactly 15 minutes, and we'll get into like machine learning and natural language processing and streaming for the last hour. All right, guys, we're in the last home stretch. So there is one thing I want to point out. I'll probably end up going to about like 5:15, something like that, maybe 5:10. But anybody who might need to leave early, I just want to mention that in the class notes document, there is a post-class survey here on page 2. If you're going to hang around until 5, then don't bother doing it right now. But if you're going to take off early, please try to complete that before you leave. Okay, so for everybody else, what we're going to do is we're going to, before I give a short lecture on machine learning, before that, what we're going to do is open up this 08 notebook for fundamentals of natural language processing. So go ahead and open up this 08 notebook. And attach it. It looks like I actually lost my cluster, so I'm just going to launch a new one, Samir demo, create cluster, and now it should be launching and getting attached. And this specific notebook, this is just a setup to the next machine learning notebook. So we're going to kind of just quickly skim through this notebook, run a few of these commands so you get a sense of what the data set looks like. Then I'm going to do like a 10-minute lecture on unsupervised machine learning, and then we're going to actually implement the stuff from that lecture. Okay, so it looks like that cluster should be starting up for me. Okay, there we go. It's up. And we're going to attach to it. Okay, what I'm going to do actually, just for to keep things interesting, you can just continue using Databricks Community Edition and use that cluster. However, what I'm going to do is, let me show you in just a second. Okay, here we go. Okay, here's what I'm going to do. Just to keep things interesting, I'm not going to run on Databricks Community Edition. I have a larger cluster running, and I'm just going to run on a larger cluster to have these commands complete a little bit faster, and also so you can see what an environment of like a larger cluster looks like. Here I have a cluster with only 2 executors. Actually, one of them is a driver. That's why it shows up as 3. It counts the driver as an executor. And then I really have only 2 executors here and a driver. Okay, so I'm going to actually run on this cluster, and each one of these executors has 4 cores, so there's really 8 cores total. Okay, so let me stay here, and I'm attached to my standalone cluster. You can be attached to your local mode cluster if you want. Okay, let's quickly answer some of these questions. What we're doing here is actually looking at English Wikipedia itself. If you run this command, then there's a, what I did here is from the March 5th snapshot of English Wikipedia, the March 5th snapshot is 54 gigs. It's a little bit too big to analyze with the local mode cluster. So what I did is I took the March 5th snapshot, and then I basically kept only the articles that were last edited between March 3rd and March 5th. So basically, I got the March 5th snapshot, then I kept only the articles that were last touched in the 3 days before March 5th. Then I took the 100,000 articles from that, and I made a Parquet file with basically 30 Parquet files, or a Parquet folder with 30 Parquet files. So that's what these are. These are just Parquet files. And they basically amount to about 660 megabytes. So let me go ahead and read that data, all 30 partitions. I want to cache this data frame as well. And we're going to call this WikiDF. This is Wikipedia data frame. And if I look at the schema here, you'll notice there's a Wikipedia ID, title, text is the actual Wikipedia text. I'll just show you a few of the columns here. So this is going to show me 5 articles. So this is, like I said, a setup to a more sophisticated machine learning lab we're going to do in just a second. Okay, this is like showing this data. There's the Wikipedia ID, title, the last revision time for the last time the article was touched, revision ID, and then if the last revision was made by an anonymous user, you'd get the contributor IP there. And this is the full text of the article, the way it looked like on March 5th. This is this row here doesn't have a contributor IP. This is null because this article was last touched by a logged in username. Okay, so this is what the data looks like. I'm going to do a count to materialize the cache, to read all 30 partitions from disk, and to build up my cache in memory of the 30 partitions. So like I said, this is going to run a little bit faster for me because I'm running a different cluster that has 2 executors. This might run a little bit slower for you. So see, I can run eight tasks simultaneously. You can only run 3 at a time because you have a local mode cluster. Okay, this is going to tell me how many Wikipedia articles I have. It's 111,000. So we're not working on all 5 million articles. We're working on a subset of that, 100,000 articles approximately, which would take up about 1.9 gigabytes. The reason for this is, if you remember, in local mode Spark cluster, you only have 2.4 gigabytes available for caching, which is why I took a subset that would be under 2 gigs. Okay, now that I'm in memory, I can do a count, and I can see that I can do a full scan in memory under a second. I'll register a table called Wikipedia, so I can do SQL queries. How many days of data is in the data frame? Okay, I'm just going to give you the answer for some of these so we can move faster. This is pretty simple, right? We just need to import our Spark SQL functions, and then on the last revision time column, we're going to call the day of year and do distinct and show. This should just say 3 days, because I made a subset of 3 days worth of data. This is like March 3rd, 4th, and 5th. Here are some of the random articles and when they were last edited. Okay, next question. How many of the 111,000 articles were last edited by ClueBot NG, the anti-vandalism bot? So we'll do a SQL query here, like this. Select count all from Wikipedia where the contributor username is ClueBotNG. And here, I'll do a limit 10. Actually, before that, since I'm doing a count, I don't think I need to do that. There we go. So it's 1,200 articles out of the 111,000 were last touched by an anti-vandalism bot. Which user in the 111,000 articles was the editor of the most articles, was the last editor of the most articles? So here's the query. Select username and the count of the username from Wikipedia, group by username, order by the count of the username. This is going to basically show us which user touched the articles the most out of the 111,000. You'll notice by skimming through the username list and the count of how many articles that user last touched, there's a whole bunch of bots here. Casper bot, side bot. So you can learn more about these bots by just doing a search on Wikipedia about them. All the bots have a user page where you can learn more about them. Okay. We'll skip question 4 completely, and let's skim down to question 5. What we're going to do here is the beginnings of machine learning. We're going to import from Spark ML the regex tokenizer, and we're going to basically make a bag of words for every Wikipedia article. So what we do is we take the text column, that's the input column, and we're going to make a new column called words. And the pattern here is just to extract out the word out of the text. Let's go ahead and run this, and we're going to get a new data frame called WikiWords data frame. And this WikiWords data frame, it should have a new column called words. Let's look. There it is. That's the words column. And I can see here on the left is the text column and then the words column. So this is, for example, the text column. Notice it has like these funny characters before info box. But here, I actually have just the word info box. So I basically extracted out a bag of words by simply running, these few lines of code.
And our input was XML
our input was not XML. Our input looked like this. This is what our input was. This is what the text column had in it. Okay, now that I have a bag of words, I can just show you some of those words for the first article. For this new Las Cruces, New Mexico article, here is the bag of words for that article. So it looks pretty clean. It got rid of like the random characters and stuff in Wikipedia for articles. Okay, now I have a bag of words. This is like usually the first step in doing natural language processing or machine learning on text. Let's answer this question. What are the top 15 most common words in the English language? We'll do this by first downsampling the wiki words data frame into a 10% sample, and then we should get about 11,000 articles. So for something like this type of question, we don't need to do it on the full data. We can still get an idea of what are the most common words by looking at just 10% of the data. So this is how you do a sample on a data frame. And then if I do a count, I have now 11,000 articles. This is saying give me 10,000, just 10% of the data, and this is just a seed. Now if I select words out, that's actually the words column, you'll see that the words column has an array of strings. Those are all the words. Finally, what I can do is this. On the 10% data frame, I'm going to select words and I'm going to explode it. So this is an interesting Spark SQL function. Explode it as words. It becomes more easy to see what will happen here when I just, let me just show you what this new data frame has in it after the words explosion. Here we go. See what I just did? I kind of just pivoted. I took all the words in all the articles. Right? I took all the words in all the articles and I put one word on every row. So now I have a data frame that is like, I don't know how many rows this is. Let's check. I guess it's going to be about 30 million rows. So I have about 30 million words so far. So from 11,000 articles, I extracted out 30 million words. Okay, and it was like just like 10 lines of code to do that. And I'm just caching all those words in memory. And then I'm going to do a word count. So this is interesting. We're doing a word count using data frame. So I take that 10 words data frame. Let me just show you what that data frame looks like. I'll do a show 2 on it. This is just the data frame, right? Then I'm grouping by word, and then I'm doing an aggregation, and then I'm doing a sort. That's it. And then let's look at the top 15. Anybody want to venture a guess what the top 3 will be? Exactly. They're the same words you would... The, of, and. They're the same words you would see in the English language if you're looking at anything. These are like stop words. The, of, and always appear the most. And actually, this one is a Wikipedia-specific type of word. REF shows up in like in the text of Wikipedia a lot. HTTP is also a Wikipedia thing. Title is a Wikipedia thing. These are basically stop words, though. It would be nice to get rid of these. So, to get rid of those stop words, we can use the stop words remover. So this will take input of the words column and create a new column called no stop words that has all the words without the stop words. So let's run this. And then we're going to just basically look at how I run it. I have this remover function. And on remover, I'm calling transform, and I'm giving it a data frame. And this gives me back a data frame that has a new column called no stop words. And I'm printing out some of that column here. So here we go. Did it remove stop words? Yeah, see here, the word about and the got removed. From the words column, it got removed, and now in no stop words, those two words don't appear. Also here, the word about got removed. Okay, so we got rid of stop words. And now, if I continue, now on this no stop words data frame, if I do show 7, these are the words without the stop words. Now let me do a count. So remember, there were 29 million words before. If I remove stop words, then I'll have like 22 million words. And then let's look at the top 15 words after this. I'll just go ahead and run that cell as well. And like I said, this is going to run a little bit slower for you in Community Edition. If you're falling behind, just switch to the README version of the notebook. Or it's getting late, you can just kind of watch what I'm doing as a demo, and you can go back to the stuff later on. Okay, 22 million words remaining. These are those words. They still look like, you know, these are Wikipedia-specific words. Right? None of these are really interesting. Okay, how many distinct words do we have now after we removed stop words? 700,000 or so, 716,000. This is the range of the vocabulary out of the 11,000 articles that we're looking at right now. Remember, we took a sample of the 111,000, 10% sample gives us 11,000 articles. The distinct number of words that we have is about 700,000 right now. So this is the end of this lab. But one thing you should know is we're working on a data set that has too many unique words because we're looking at an encyclopedia. Does anybody know that if you actually look at just one book by an author, and if you do a distinct word count on that, does anybody know roughly how many words you would see? If you just let's say you pick the first book from Harry Potter, and you do distinct word count, how many unique words would there be? It's about 4,000 to 7,000 is the range of an author. This is encyclopedia, so the range is almost like 1 million unique words. We're going to have to do dimensionality reduction before we do anything sophisticated from a machine learning perspective here. So we're going to take it from a feature space of 700,000 unique words, and we'll do dimensionality reduction and bring it down to 20,000, and then we'll do TF-IDF and k-means clustering on this. So I have a short lecture for machine learning. That's like a quick 10-minute lecture I want to do just to set the stage for the next notebook. So let's talk a little bit really quickly about machine learning. How many people here have done anything with Spark machine learning? Oh, a bunch of people. Okay. What about with Spark ML, the new DataFrames version of Spark machine learning? Okay, maybe 5 or 6 people. Okay. So Spark machine learning, it's inspired by scikit-learn, and the whole goal here is to make machine learning scalable and easy to use. This is a picture of me at Facebook, actually, a while back when we were doing a class on machine learning. So there's a lot of algorithms in Spark machine learning. I'll let you skim through this for a second. This list is based on Spark 1.6. We're going to look at just 2 or 3 of these algorithms right now. Basically, this is the high-level functionality in Spark's machine learning library. There's learning tasks, data utilities, and workflow utilities. Okay, once again, just kind of skim through this. At the very high level, there's 2 components in Spark MLlib. The older one is called Spark MLlib. This is the package. This is the old API built on top of RDDs. This is going into maintenance mode in Spark 2.0. So you want to actually be using Spark.ml. This is the new library built on top of DataFrames that uses Spark's Catalyst optimizer. So this is what we're going to demo right now. And what we're going to do is we're going to basically do TF-IDF and k-means clustering. How many people here have used TF-IDF before hands-on? About 15 people, maybe 20% of the audience. How many people here have done k-means clustering hands-on? About 30% of the audience. Okay, cool. I'm going to teach you the math really quickly of TF-IDF. Then I'm going to tell you the intuition behind k-means clustering. And then we're going to basically do TF-IDF and k-means clustering in a quick demo notebook. Okay, TF-IDF, here's how it works. It stands for term frequency, inverse document frequency. The idea here is we want to build like a search engine. And the way this works is when you want to build a search engine and you want to like find articles in Wikipedia that have the word elephant in it, for example, then TF basically means if a word appears frequently in a document, it's important. So if a document, like an article, has the word elephant 20 times, that article in Wikipedia is maybe about elephants. However, IDF means if a word appears in many documents, like the, and, or of, then the word is not meaningful and lower its score. Let me show you that in an example. We have 3 sample articles here in Wikipedia. This article sample has 6 words. This one has 3, 4, 5, 6, 7 words. Let's calculate the TF score for these 3 articles. Remember, TF is just the number of time a word appears in a document divided by the total number of words in that document. Okay, so let's do that for like the word the. The word the appears here twice, so 2 divided by 6. Okay, so the word the appears twice, divided by 6 because there's 6 words here, and the TF score is 0.3. Politics appears once, 6 words, politics TF score is 0.16. Over here, sports appears twice, and there's 3, 4, 5, 6 words here, so 2 divided by 6, TF score is 0.3. That's all you do for TF. But notice right now that if you do this, in green now, we have a bunch of stop words that are appearing. So if you just try to build a search engine, and I've sorted this here by the TF score. But if you build a search engine and just say on the TF score, then incorrectly these stop words are kind of bubbling up too high. So we need to knock off the score of the stop words. That's where IDF comes in. IDF, the way you do the math here is total number of documents, so 3, divided by the number of documents with the word X in it. And then we just get the log of that. So basically, total number of documents is 3, right? And then if you want to do this for the word the appears in every document. So we're going to do 3 documents, divided by 3 because the word the appears in 3 documents. Log of that is 0. If you do the same thing for politics, politics appears in 2 documents. There's 3 documents total. Politics appears in 2. IDF score is 0.18. You do the same thing for sports. It appears in 1 document out of 3. IDF score is a little bit higher, 0.48. So you just basically do this for all the documents and all the words, and you generate the IDF score. And then to generate the TF-IDF score, all you do is TF times IDF. And then you get that number. This is the TF score from before for politics with the politics IDF score, and then you get that. And now you can see that in general we see unique words at the top, not really stop words. I guess here of is appearing, but that would be cleaned out in a real data set. So now we have a trivial search engine. We can type in like the word sports, and for sports this should appear. This should like bubble up because this is where sports is ranked the highest. Or if you like type in politics, then politics is number 2 here and number 3 here, so politics should appear in our search engine. So that's where TF-IDF is. K-means clustering. I'm just going to tell you the intuition behind this, of how this works. In K-means clustering, K is the number of pre-chosen groups. So the way this works is maybe we want to do K equals 2. We want to take these 8 articles and cluster them in K equals 2 clusters, into 2 clusters. So you want to take the sports article and put it in the sports cluster. You want to take this politics article and put it there, and organize our documents like this. So the idea here is to basically unleash unsupervised machine learning on all 5 million articles and maybe cluster them in 100 clusters and see if this will automatically make intelligent clusters for us. Maybe we'll make 1 cluster for politics, 1 cluster for sports, which would basically let us organize the data in Wikipedia. Now, really, in a real cluster, I would use something like 10,000 clusters, right? 100 seems a little bit low, but we'll try it with 100, and we'll do it on our sample of the 111,000 articles. And that's really all we're going to do. I'm going to skip some of these slides because they're kind of explaining how k-means clustering works behind the scenes. So I don't want to really get into this. Maybe what I'll mention here in general is that the initialization that we use in Spark for k-means clustering is k-means parallel. So if you don't use k-means ++ and we don't use the standard algorithm to select the initial centroids, we use k-means parallel to do this. That's really all I want to mention. I'm not going to get into the math of k-means clustering. Instead, what I'm going to do is one last slide, which is this one. We're going to build out a ML pipeline here. The way an ML pipeline works is we're going to take an original data frame, flow it through the pipeline. And as it goes through the pipeline, it's going to keep giving me a new data frame with a new column attached. And at the very end, when it comes out of the pipeline, that data frame is going to have like 7 or 8 new columns. That's the fundamental thing you should understand about ML pipelines. In the ML pipeline, we're going to have either a transformer or an estimator. And they're going to just keep adding new columns. A transformer adds a new column, and an estimator adds a new column. Let me show you this in the real-world example. This is our original WikiDF data frame. We pass it in through the pipeline. This is the whole pipeline of ML pipelines. As you can see, as it goes through these different steps, a new data frame just keeps coming out. And basically, what we're doing is we're going to take the lower text column, pass it through the tokenizer transformer, and we're going to get the words data frame. The words column. So this data frame right here basically has a new column called words. This data frame goes through stop words remover. This one reads the words column, runs the transformer for stop words remover, and it gives me a new column called no stop words. So this data frame here has two new columns, no stop words and words. So what we're doing is we just keep adding on new columns here. We take no stop words and we get a hashing TF column. We take the hashing TF column, we get an IDF column with this estimator. The IDF column goes in, we get a features column, and from the features column we get the prediction. The prediction is basically going to be a number between 1 through 100, and that will tell us which K cluster it's going into. So this is basically the ML pipeline. Notice here in hashing TF, we're taking the feature space of something like 700,000 words, and we're doing dimensionality reduction to bring it down to only 20,000 features. So what this means is sometimes, like on the left side, the word elephant and the word blue might get hashed to the same feature here. Right, that's kind of what we're doing. So 2 or 3 words or 10 words might get hashed to just the same feature on the left. And this is going to give us slightly less accurate results, but this is what we need to do to actually run machine learning at scale. Yes?
Is the interface open to write one's own transformers? Say I wanted to classify, IT articles where maybe the terms Microsoft and Google would be very common, and I want to add them to the stopwords removers or like.
You can do custom stop words remover as well. There's a way in the stop words remover to give it custom words to also remove.
In general, right, like my own box in there, and just plug it in, whatever it is.
You can make your own box here as well. You can insert your own special thing in here. Yes. Let me show you this through the example. I think this will make it a little bit simpler to do. What I actually recommend you guys to do right now is I actually recommend you guys to go to Workspace and go to the README version of 09, because some of these cells are going to take like 2 or 3 minutes to run, which is a little bit slow. So it might be easier for you to follow along with just like the README version, which has the output already there, just for sake of time. And then you can run this as a RunMe version later if you want. But just for sake of time, it might be useful for you to go to the README version. What I'm going to do actually is I have a cluster here running with 20 executors. I'm going to run this live on that cluster. So I will go to 09 data science wiki ML, and I'm going to attach this notebook to that 20 executor cluster, just to like show you guys this stuff at scale. Where is it? There is my Samir 20 executor cluster. I'll close this old UI. I'll go and start reading that data frame here. And now it's being read. And what I'll do is I'll just show you the 20 executors really quick. Executors. So see, now I'm running like on a pretty big cluster here. And I have 8 cores on every executor. So that means I have 8 cores times 20. I have 160 slots on this cluster. So since I have 160 slots on this cluster, what I actually want to do is I actually don't want this data frame with only 30 partitions. What I'm actually going to do is unpersist that data frame with 30 partitions, and I'll put a repartition in here. Repartition it to a data frame with 160 I'll use 160 partitions here, and then I'll cache it, right? Because I have 30 partitions in my part K file, which will give me a data frame with 30 partitions, but then I'm going to repartition to 30, and then I'm going to cache it. Okay, so it is kind of expensive, but it's going to make my machine learning run faster, so I'd rather incur that cost right now. So here's the columns that I have. This is the same wiki data frame we were looking at earlier from the exact same data set. So this is going to show me a few columns really quick. Let me run this show command.
You repartitioned without knowing the 50 to 200 megabyte partition.
I did. I cheated because this is a compute-intensive operation, so I need as many partitions as possible, and I'm going to optimize for that as opposed to the size of the partition for this use case. So I do show 5. This is what our data looks like. It looks very similar to before. I'm also going to do a count really quick just to materialize everything in memory, and then we can go and see how big this stuff is. Here's our data frame. It's 100% in memory. 160 partitions, total size of about 2 gigs, and each partition right now is about 100 megabytes right now, each partition. Actually, no, this is how much data is on the executors. Each executor has 100 megabytes of data. Down here is the partitions. My partitions are pretty small, 12 megabytes in memory. Let's just see how this works. I actually haven't run this with this specific configuration before. What I'm going to do first is on my data frame, I'm going to just lowercase all the text and make this column called lower text. So let me just show you the data frame now. So see, I have the exact same data frame we saw before. This is my text column. This is my lower text column. The lower text column is what we're going to pass in to our pipeline. Remember this slide? It starts with lower text and gives you a column called words. Words column gives you a column called no stop words. Or just keep this in mind. We're gonna, in a second, we're gonna look at this prediction column. It's not really too critical. Maybe for production, I would drop columns that I don't need, indeed. For this use case, it doesn't really matter. This is just a proof of concept, right? But yeah, you'd probably do that in production. Okay, so what I want you to take out of this is just how easy it is going to be. It's going to be about 15 or 20 lines of code to build out the full ML pipeline, and then we'll be able to see the prediction. It's going to tell us this article goes in K, this number, K2. This other article goes in K equals 35. So let's do that really quick. This is my imports. I'm going to import regex tokenizer, stop words remover, hashing TF, and IDF, and normalizer. Step 1, I need to take my lower text column and make a bag of words. So I'm going to use the regex tokenizer to do that. I'm passing in my wiki lower data frame. From that, the lower text will be analyzed, that column, And we're just going to do this regex tokenizer and get the words column back out. So now this data frame should have one new column. Let's print schema and check. It should have a new column called words. There it is. Right? So we went from lower text to words. Let me show you that. So here's like the first row. I'm just selecting out the words. So for this article, or I'm not sure which article this is. This is just this is like the first article. I'm just looking at the words. It looks like it's a Science article. Okay. Next step after that is from the words column, I'm going to generate a no stop words column. So let me run that. I have a new data frame now called no stop words. So now this data frame, when I print schema, I should see one new column. There we go, no stop words column, right? Let's look at some of the results. There we go. This is the article ID, title. These are the normal words, but this is the no stop words. So notice here the words for and the have been removed. Okay, that's good. Let's run hashing TF next. I take the no stop words column and I want a new column called hashing TF. It's doing dimensionality reduction down from like 1 million features down to just 20,000 features. Because the number of unique words I have in all of Wikipedia is probably like 1.5 million. I don't want that many columns in my vector. I want only 20,000 so that I can compute this in a reasonable amount of time. So let me print schema now, and I should have a new column called hashing TF that should have a vector in it, and that vector can have a number of like 20,000 numbers. Let me show you that vector. Look here, I'm just printing out the ID, the title, no stop words, and hashing TF. And let me just also do I'll do a limit 2 and wrap this whole thing in a display. And then I can actually show you that vector a little bit better. That's the no stop words. I actually don't want to see that one. I want to see, yeah, that's the vector right there for hashing TF. This is the new column that we made. So in like this is a 20,000 feature space vector, and I can see that like at number 0, there's 6 words that got hashed there. Okay, so we have a vector now. So we took words, we got math out of it, we got a vector. Next step is IDF. Let's run that. We should get a new column now called IDF. IDF is a model. So there's our IDF model. Next, we take the IDF column and we generate the features. This is normalizing. This is basically just some articles are much larger than other articles, so we have to do normalization. And then finally, we do k-means. So there's something I need to point out here. This step 6, where we actually do the full pipeline. See, we're actually like running the actual pipeline here. This takes a long time. In Community Edition, this is going to take more than an hour to run, probably take a few hours. So there's a little trick I have here. The trick is I actually ran this code, this exact code, in a 50-worker cluster like a month ago, and I built a model off of all 5.1 million articles, and then I saved that model to S3. So instead of running this, which is going to take hours to run, what we'll do is we'll load our model that I build from all 5 million articles with k equals 100, and we're just going to load that model 2 up here. And this is the model that we're going to actually run with, because this is going to save us a lot of time. I'll show you what's in this folder really quick if you're curious. So we're going into the Wikipedia read-only folder and then models. Here it is. This is the model that I just created off of the 5.1 million articles. So if I go to like metadata there, that's really nothing there except for that file. Here's the stages. So my model has the regex tokenizer information, stop words. If I go into the metadata there, there's some data there. So what else is in here? Stages. There's IDF, normalizer, and k-mean. So my model has basically like the full pipeline information. This model is not too big. I think it's like maybe a 20 or 30 megabytes. So I'm sidestepping, doing the hard work. I'm loading my model that I built that's a little bit more accurate, right? I built it off of 5 million articles, not 100,000. And now I'm going to apply my model. So on my model, I'm just passing in my original data frame, the wiki lower data frame. This model expects the data frame to have a column name with lower text, like that. It needs this, and this is basically the model that I just loaded up. Okay, so let's see if this works. I'm going to run that. Let's look at the columns that come out of the model. All of these. This prediction column is what I care about. Let's show 2 results that ran really fast because it's just applying a model. I didn't have to build a model. See this 71? It aligns to the prediction column. That means that this first article for the Popeye video game went to like cluster 71. Here, let's do this. Take the predictions data frame. That's what we just ran, right? We just basically said, give me a predictions data frame, run the model on my original data frame, give me this new data frame that's going to have like 7 more columns on it. Okay? And then do group by, prediction, count, show 100. This should tell me how many of the 100,000 articles went into each of the clusters. So this is going to run pretty fast because I'm running it on a pretty big cluster. Okay, K31 got 154 articles out of the 111,000. This cluster 34 got 563 articles. Interestingly, this cluster only got 7 articles. This cluster 37 got 17,000 articles. So let's see if this makes sense. I want to filter down to just the cluster 31 and show me 30 articles here. So let me run that. So this is running a Spark job with, so this is like basically reading the original Parquet file. And there we go. It runs pretty fast. Let's see if it makes sense. So I had to manually classify this. This seems to be like Indonesia and Asian articles in cluster 31. Let's look at the next cluster. This is cluster 32. And this seems to be like Norway or like Scandinavian, like Nordic articles, it seems. It put in cluster 32. Norwegian literature. This looks like a Norwegian name. So it does seem to do that classification, districts of Norway. 45, like baseball got its own cluster. So these were like famous baseball players and things like Major League Baseball.
I have a question. So did you specify a seed value? So how come it's always the same cluster?
What do you mean? How come?
Numbers, how come it's always, so where did you specify?
The cluster number I'm manually typing in every time I'm doing this query.
You have to specify the seed value to get the same cluster.
K equals 100, you mean?
No.
The seed?
Seed for the random.
Oh, well, I think that has to do with my model. My model itself has that built into it, I believe, right now. Yeah. I didn't specify that manually. It's just built into my model. That was baseball. This seemed, 82 seemed to be like music and film. And you know, this is probably not the most accurate way of doing clustering. I didn't like really do this carefully. My point was just to make a proof of concept to do this quickly. So this one seems to be like music and film. By the way, one of the clusters ends up getting something like 20% of the data. Like, I can't remember which one it is, but one of the clusters gets like 15,000 articles out of the 100,000. So, you know, there's like some more cleaning in the data I would do. I would probably do k equals 10,000 or 15,000 to do this accurately. Here's like singers and actors. This is politics. I'll just go ahead and run this really quick. singers and actors in that cluster. This one seems to be politics. I thought it would be actually interesting to find where Apache Spark goes. So here I'm filtering it out to Apache Spark and then finding basically which cluster did it put Spark in. It put Spark in cluster 5. And then I thought it'd be cool to kind of see what are the other articles in cluster 5. Like, are they going to contain like technology, software articles, big data articles? Let's see. It seemed to be like kind of technology-related articles, like Windows RT, text mining software, Siemens software, secure shell, 3Com, data discrimination. So it did put Apache Spark in a cluster with a bunch of technology articles. So it did seem to classify that correctly. So anyway, that's the whole point of this short exercise, simply to show you that you can do this. My colleague actually did the same thing here with the Enron email files. So he was able to like classify, he just basically copied and pasted the code. He had the Enron data at one end of it, and he was able to cluster the Enron data into 100 different clusters and find certain topics in different clusters. So if you're like, basically, maybe you're doing some investigation, and you want to find all the emails that refer to a specific topic. So maybe you would do that with emails, and then you'd find that topic, and then from that, you can go deeper into all those email subjects and find out what you're looking for, perhaps. Okay, so hopefully you'll find this code interesting, and you'll be able to play around with it on your own time. Any questions about any of that machine learning stuff? Okay. We have about like 15 more minutes. I'm probably going to take 25 minutes to wrap up, if that's okay with everyone. I'll go like probably 10 minutes over. Yes? Exactly at 5? By what time? 5:15? Okay, perfect. All right. Okay. So let's wrap up with a little bit about Spark streaming. Okay, so what I'm going to do with Spark streaming is I'm basically going to just build out a really quick prototype of Spark streaming to do some analysis of the English language stream versus the German language stream. And we can do this actually really quickly. How many people here have written a Spark streaming application at all? Just want to get a sense. Oh, wow, very few people, only about 6 or 7 people. You might be pleasantly surprised at how easy this is to do. It takes like 7 lines of code. What Spark streaming is going to do is it's going to give us an RDD every batch interval. So we'll set our batch interval to 3 seconds. And what that's going to do is on the English stream, whatever edits happened within a 3-second batch, that will give us an RDD. So every 3 seconds, we get an RDD for English. Over here, we're going to be looking at the German stream, also with the 3-second batch interval. And every 3 seconds, we'll get an RDD with the German edits for whatever happened in that 3-second window, or 3-second batch. So we'll get 2 RDDs every 3 seconds. And then what we'll do is we'll take the RDDs and we'll just build out some dynamic graphs to do some analysis to understand how many edits are happening for English versus German. And I hope that you'll see how easy this is to do. There's really one important takeaway I want you to get from this. You're all new to Spark streaming. The most important thing you should know about Spark streaming is how to make a stable Spark streaming application. It's really simple to understand. Stability condition for any streaming application is receive data only as fast as you can process it. In the lingo of Spark streaming, that means finish processing the previous batches before the next one arrives. So you're getting an RDD every 3 seconds, right? Every 3 seconds you're getting an RDD. And you're going to process these RDDs in order. If it's taking you 4 seconds to process an RDD, you're going to start falling behind. Where eventually when an RDD gets created, you're going to have to wait like 15 minutes before you can process it because you have to process all the earlier RDDs first. That means you have an unstable application. That is the most important thing you need to understand. That, here, let me show you that in diagrams. Here, we have a batch interval of 2 seconds. So look, we go from like 0 seconds to 2, 4, 6, 8. Our batch interval is 2 seconds in this diagram. Now, here, what's happening is every time we get an RDD, in green, we're processing that RDD in only 1 second. So this is good. This is a stable application. Because when the next RDD arrives over here, we're ready to go to process this guy. look at an unstable application here. Here, our batch interval is still 2 seconds, but we're spending 2.1 seconds to process the RDD. This is a scheduling delay. See, over here, before we could process the RDD that got created here, we had to finish processing the RDDs that were created previously. And this is a scheduling delay. We had to wait about 1 second before we could process the RDD that got created here. This is an unstable application. I'm going to show you how to find this using the Spark UI. That is the main thing you should take away from the Spark streaming section. If you get this, you'll bypass the first problem most people run into with Spark streaming. Okay, I basically have two Node.js servers running. This is a Node.js server running for English on port 9002, ending in IP address 194. Then I have another Node.js server running on IP 240 that on different ports is showing the language edit stream for these languages. So I have two Node.js servers running. What we're going to do here is we're going to, I should actually have only 3 slots here, not 4. We are going to basically listen to the English stream. We're going to run a long-running receiver. This receiver is getting this edit stream of English, and it's going to be building out an RDD. And at the end of the batch interval, we're going to get an RDD, then we're going to process that RDD. In this example, the batch interval is 600 milliseconds. In this example, we're done processing it within about 400 milliseconds. While we're processing this first RDD that got created, another RDD will be coming in that's being built out. And by the time this RDD is ready to be processed, notice we're done processing the earlier RDD. And then we process this RDD, and then we start building out the next RDD. So the main point in this slide is the English stream is going to be using the older receiver-based technology, which is going to be eating up one of our 3 slots. If we're looking at 2 different language streams, let me just jump to the other slide here. If we are looking at 2 different language streams, then we're going to be eating up 2 of our 3 slots. Right? So this is something important. This is a limitation of the receiver-based technology. If you use something like the Kafka direct pull approach, it won't use receivers, and it will not eat up slots permanently like this. That's how you should do it in production. I'm just showing you this as a proof of concept. So we're going to use 2 receivers, one for English, one for actually German. Then we're going to have only 1 slot remaining for doing processing of the 2 RDDs coming out of these 2 receivers. And we're going to do a batch interval of 3 seconds. Right now in Spark 1.6, you're going to get an RDD every batch interval. In Spark 2.0, you'll be able to get a data frame every batch interval. Okay, let's just run this. Let's just kind of run the code and see what happens. I think you'll be pleasantly surprised at how quick and simple this is to do. I'm going to go to Run Me, and I'm going to go down to streaming number 10 here. So this is something you might want to follow along with. We can get this done in like 2 minutes for this notebook. So just go to Data Analyst Streaming 10, connect to your notebook, to your cluster. And one thing that's really important to do is to open up your UI. And notice when I open up the UI, up here, I don't see a button for streaming. That's going to show up in just a second. After I start Spark streaming, a new button is going to show up, or a new link. Okay, how many edits occur to English versus another language every 3 seconds? It's a pretty simple business question. Let's say English versus German. Do your imports. And then we're going to set batch interval to 3 seconds. And we're going to set an English streaming server, and we're going to set a miscellaneous language server. This has nothing to do with Spark streaming. This is just setting some values and variables. Okay, let's run that. Okay, next, to make a Spark streaming context, we're going to take our Spark context, and we're going to combine it with the 3-second batch interval. And then we get a streaming context that we'll assign to SSC, Spark Streaming Context. Okay, we're almost ready. Now what we'll do is we'll take the Spark Streaming Context, and we will listen on the English IP address, and the English port. And then we will get a base English dstream. Let's run that. And let's do this for the German dstream. We're listening to the miscellaneous language server IP address and the German port. And then we'll get a German dstream. What is a dstream? A dstream is just this abstract concept. What it means, what a dstream means is basically, every batch interval, we're going to get an RDD. And then on that RDD, we're going to do some transformations. And we're going to get a different dstream as that's happening. The main idea here is if you do your transformations on a dstream, then it applies the transformations to the RDD that's being created every batch interval. So what a dstream means, it's a continuous flow of new RDDs. A dstream is basically just new RDDs being created every batch interval. And if you take a dstream and you do a filter on it, then what that, like right here, what that means is you're doing this filter on the RDD that's being created every batch interval. So every 3 seconds, you're doing a filter on the RDD. That's what this means. So a dstream is just a flow of RDDs. And we're just doing our transformations on every RDD. Okay. We have an English dstream and a German dstream. Here's basically one of the last steps. On the English dstream, for every RDD that's being created every 3 seconds, as long as the RDD is not empty, take the RDD and read it using SQL context read JSON. Now this is interesting. This will give me a data frame because this RDD contains JSON data in it. So we're actually reading that JSON data using the Spark SQL context reader. This gives me a data frame actually, and then I'm going to register that data frame as English edits. This is it. This is all the logic I'm doing. I'm not doing like 20 transformations. I'm just taking the RDD every 3 seconds, making it a data frame, and registering it as a table. That's it. I'm doing the same thing with German down there to register a German edits table. So RDD to data frame to register a table. Okay, we're going to run this cell to remember the data for 1 minute, start our computation, and that's it. Now Spark Streaming should be running. If I run this cell, select all from English edits, these are live edits happening. And if I run it every 3 seconds, I'll see new data. Because every 3 seconds I'm getting a new RDD that I'm converting to a data frame and then registering it as this table called English edits. You see how this table is different every 3 seconds? Right? I basically, it shows me like information about the edit. Like this is delta positive means people edited data, added data in there. Delta negative means people deleted data from the article.
This table keep the last batch or the...
We're not keeping the old data. We're just deleting the old data and making a new table every 3 seconds right now. In just a second, I'm going to show you how to keep the old batch. Remember is basically keeping data for up to a minute. However, the table is still refreshing every 3 seconds. I think just hang tight. I'll show you in the next notebook something a little bit more interesting. Let me just do this. This is German edits. If I keep running this, you'll see German edits happening every 3 seconds. Let's see if that changes. There we go. Finally, let's do a count. How many English edits happened in the last 3 seconds? 5. In the last 3 seconds, 3. We can union 2 dstreams. So here we are unioning the English edit table with the German edits table. And we're counting English edits versus German edits in this 3 second period. And finally, what I can do is I can make a diagram. I can make here what I'm doing is I'm making a line chart. And actually what this gives me is really a table like this. And then I can click on the line here and I can make a line graph. Now notice this, if I keep running this every 3 seconds, see how this is changing? And English is in blue, and what this is showing me is in this 3 second period, I can see 1 second, actually 4 edits happen in this 3 second period. Let me run that one more time. Here's Basically, it's showing me that 4 edits happened on this second interval, 0 German edits happened here. But you know, this doesn't really answer my question. It's really hard for me to understand how many English versus German edits are happening on Wikipedia. This is really hard. I mean, this is an interesting diagram, but I don't want to see this in a 3-second batch interval. I would rather see this with a 1-minute window. So that's what I'm going to do next. Okay, so the last complexity I'm going to add is I'm just going to stop this. I'm going to show you the next notebook for 1 minute. There's only one new line that's changed in this next notebook. Let me attach this notebook to the cluster. It's answering the exact same question, but this chart I think you'll find really interesting. This is the same imports. The batch interval, these imports are the exact same. This is exactly the same. Making the base dstream for English and German is the exact same. This is the only difference here. Look. See here? I take the English dstream and I'm making a window of 1 minute. I'm coalescing that down to a RDD with 1 partition. And then, look, I'm taking that RDD, registering an English table. It's almost the exact same thing. I'll make this actually 1 minute as well. And here I'm registering a table called both edits with English and German. The only difference here is this window here and this window here. What this means is I want to basically keep up to 1 minute of data. So this will make more sense when I actually show you the dynamic graph. Okay, let me run this. I'm going to remember data now for 5 minutes. Start Spark streaming. Okay. Here, let's do a count all English edits. Notice now that this count is going to keep increasing. 15, 24, 27. We're going to 32. We're going to keep up to 1 minute worth of edits. After a minute, we'll start dropping the old ones. Here's English edits as well. So select all. This table is going to keep growing now. So see how it has right now like 30 seconds worth of data for English edits. Here's my German edits table. Once again, keeping up to 1 minute worth of data. And after that, it's going to delete the data older than 1 minute. So this is going to give us a little bit more interesting of a graph. This is called window analysis. Finally here, we're going to do a union between the English edits and the German edits. And I can see in the last 1 minute, we got about 8 German edits and 115 English edits. Now finally, here I'm looking at English edits. And you can review this code here, but what's more interesting is if I just keep running this, look at what's happening. We have a sliding window of 1 minute. And I can see how many, this is 60 bars because there's 60 seconds in 1 minute. And I can see at this 1 minute interval, I got, like 4 edits. Right, so as I keep changing this, this keeps moving. I can do the same thing with here German edits, I think is what this is. Actually, this is both edits. So this is pretty cool right here. Let me actually make a bar graph here. Bar graph. And now I'm going to just do Control Enter a few times. In blue, I have English, and in German, German is orange. So this basically answers my question. I'm basically getting way more English edits. And then every once in a while, I'm seeing some German edits coming in. There you go. So this kind of answers our question. We're obviously getting way more English edits, way fewer German edits. Okay, the last thing I'm going to show you before we do the survey is if I refresh this, check out what's going to happen. There's a new streaming button that just showed up. And there's right now 2 receivers running, taking up 2 slots permanently. They've been running for 2.5 minutes now. That means I have only 1 slot remaining. If I go to streaming, I've been running streaming for 3.5 minutes now, 55 batches so far, 360 records collected. Input rate shows I'm getting about 2 events per second, 2 edits per second. And if I expand this, I can see the two receivers. Receiver 0 is the English receiver. This is the German receiver. I'm getting a lot more English edits than German edits. Most important thing in the UI is this, scheduling delay. It's not going up for me. If this was a problematic, unstable application, this would look like this. It would be like the scheduling delay keeps going up. That's not happening. My scheduling delay is almost 0. That means as soon as the RDDs are appearing every 3 seconds, they're being processed. Because my processing time is only 150 milliseconds. So my batch interval, 3 seconds, processing time, tiny, 150 milliseconds. This is a stable application because I'm not doing any complicated analysis here. I'm not doing a group by, I'm not doing any crazy transformations and actions. Okay? So this is the most important thing. Make sure your processing time is less than your batch interval, and make sure your scheduling delay is close to 0. And finally, all the way at the bottom here, you can see all the batches. And you can see how many inputs are coming in every batch, and the processing time for each batch. So that's basically Spark Streaming 101. If I stop this, if I stop it, my streaming UI will go away. See how it's gone? So that's it. That's basically fundamentals of Spark streaming. Okay, I need about 6 or 7 more minutes of your time. I want to actually tell you like maybe 2 or 3 things about what you can do next, now that we kind of covered a bunch of stuff, right? There's like maybe just 2 or 3 things I want to tell you about what you can do in the future with this data and leave you with some closing remarks. This will not take long at all. It will take like 3 or 4 minutes. But before we do that, I would like to ask you to take a couple of minutes and do this post-class survey. So please take just like 1 minute to do this. After that, I'm going to leave you with just a couple of minutes of closing thoughts about where you can go with this data set in the future, and then we'll kind of call it a day. So we'll conclude in about 5 or 6 minutes. But it would really help if you could give me some honest feedback about what worked for you, what didn't work for you. And this, I guarantee you, will take you less than 30 seconds to do this survey. It's only like 4 questions, and you don't have to type anything. You just have to click like 10 or thing, click a few answers, and then just hit submit. So tiny URL, Spark Summit West, SSW, 2016-Spark-Post. I'm going to continue in about 30 seconds. Okay, I have just a few closing thoughts. Here's one of them. One of the cool things happening in Spark 2.0 is this new thing called continuous data frames, where every batch interval, you'll just get a data frame. And as the new batches come in, it's just going to keep appending to the end of that data frame. This way, you don't get an RDD that you have to convert to a data frame. That is really costly. An RDD is Java objects in memory. And if you convert an RDD to a data frame, you're converting Java objects into tungsten binary format, which is really slow. It's fast for me because this data was so small in Wikipedia. So this is one cool thing in Spark 2.0. You're going to get this new API that will give you a data frame every batch interval. This is what it looks like. So you basically like read from Kafka. You make a window, and basically this stream is a D stream. And then you can basically just, this is going to give you like an infinite data frame, essentially. TD is giving a talk on this tomorrow. It's like a 30, 40-minute talk on just streaming data frames. This is the future of Spark streaming. Try not to invest in the RDD API. If you're using Spark 2.0 and beyond, use this new API for Spark streaming. Check it out tomorrow in TD's talk. I have 2 or 3 closing thoughts on Spark. If you want to learn more about Spark, check out the Berkeley Data Analytics stack. This is the original stack from AmpLab that has a lot more products and a lot more projects. And some of these projects might eventually show up in Spark. One interesting thing about Spark is that right now in Spark, CPU is the bottleneck. So if you do workloads in Spark with machine learning and streaming, you'll notice that garbage collection will be taking up a lot of time. So in modern day big data workloads, storage and network is not the bottleneck. CPU is. This was different in Hadoop about 5 years ago. So in the current generation of hardware, in the last 5 years, we've gotten a 10x improvement in storage and network, but not in single core CPUs. So the idea behind Project Tungsten, and there's going to be some talks today, in the next couple of days in this conference. If you want to learn how Project Tungsten is speeding up the CPU in Spark using these techniques, check out Project Tungsten talks. Project Tungsten is a new architecture in Spark, and it comes to maturity in Spark 2.0. In Spark 1.6, you got phase 1 of Tungsten. In Spark 2.0, there's a 10x improvement from Spark 1.6 to Spark 2.0. There's a 10x improvement because the second part of Project Tungsten is finally now available in Project Tungsten in 2.0. Okay. The main thing in 2.0 is whole stage code generation. That's what gives you that 10x improvement. In Spark 1.6, you basically have the Tungsten binary format and a few of the earlier optimizations. Okay, the last thing I want to leave you with is this. This is showing Spark 1.5 or Spark 1.6, where you have a Python API, Java Scala API, and R API. It goes to Catalyst, and it runs in a JVM. But this is going to be the future of Spark now. Check this out. Like, have you guys seen this X1 instance from Amazon? It has 2 terabytes of memory. This just came active about 2 or 3 weeks ago. What this essentially means is that 90% of big data workloads can now be done on one machine in Amazon. So this is one of the new hardware trends in big data, a 2 terabyte machine from Amazon. Another hardware trend is new types of memory like 3D XPoint. This is a new thing that Intel and Micron announced in July 2015. The materials and physics of this hardware have not been released. However, this is basically, this technology has the capacity of SSD, so you can have like a terabyte amount of data, but the latency of flash memory, so the latency of on-chip RAM, but the storage of SSD. So this is also a new thing coming in the future in the next few years. So what will Spark 3.0 and 4.0 look like? Something like this. You'll have higher level language bindings, and maybe you'll get 2 or 3 more language bindings at the top. Everything in the future will always go through Catalyst, and the runtime engines might not just be JVMs in the future. In the future, you might be able to run code directly on 3D XPoint or in LLVM or SMID. Right, so this is where the future of Spark is going. Different Tungsten backend engines in the future. Everything will go to Catalyst, and there'll be maybe some new language bindings. Okay, that's it for Spark. I have 2 more slides. Wikipedia, remember the first thing I said about Wikipedia, 5 million articles? The goal of Wikipedia, though, was to cover the sum of all human knowledge. How much will that be? So I did a Google search on how many articles you need for the sum of all human knowledge. It's 104 million. There's a Wikipedia article on it. So Wikipedia has a long way to go as well. And so, you know, this is going to be another 10, 20, 30-year project to add more data. I thought Wikipedia was really interesting because this has been a human obsession to, you know, gather all of human knowledge together. It burned down the first 2 times it was attempted, right? It burned down in the Library of Alexandria, and the Roman Empire attempt to burn down. The word encyclopedia comes from the 1700s French attempt to do this. The main challenges Wikipedia has is the rise of smartphones. People don't edit Wikipedia from their cell phone. That means there's a decline in the number of editors. This is a big problem. Another big problem is, as you saw, sock puppets, bias, and paid editors. When you're talking about the 7th most popular website on the planet, it gets attacked by vandalism, and it gets attacked by paid editors and bias. So Wikipedia has its own challenges in the next 10, 20, 30 years. And that's really all I had. Check out these 2 books. Actually, these 2 books are both outdated right now. Learning Spark is all about RDDs, and I've been telling you all day, don't use RDDs. So that means forget about that book. In this book, the problem is this Advanced Spark Analytics book, which was great, but it uses the RDD-based machine learning library. So this uses spark.mllib, not the new spark.ml. So forget about maybe that as well, but this does have a chapter 6 for Wikipedia and sentiment analysis. Maybe you can check that out. We are going to work on a definitive guide for Spark with O'Reilly. It's going to probably be a 6-month to a year-long project. It's going to be like a 400 or 500 page book, Spark the Definitive Guide for Spark 2.0. That will probably be the best place to start learning about Spark 2.0, but that's going to be a work in progress. That's it. I hope you enjoyed the class. I'll see you at the conference in the next couple of days.